I can see that our director has joined. Has Mr. Sardana joined?
No, sir, not yet.
No,
Not yet? Okay.
Let's wait. We still have time.
Yeah, there's just 3 minutes. I'll message you.
Yeah, let's wait for him.
Yeah, I'll just message him and see.
चालू है यार सीता
Mr. Sardana says he's joined. Yeah, yes, we can see him. Right. Okay, so we're ready to start. Clearly? Yes, we can hear you clearly.
Thank you.
Good afternoon, everyone. First of all, I welcome and thank all of you for being here with us today in the virtual event of Energy Day 2021, organized by the Department of Energy Science and Engineering, IIT Bombay. To begin with the session, I request Mr. Rikin Shah, General Secretary of the department, to introduce all our participants and attendees about today's session. Over to you, Rikin.
Good afternoon, all. Thank you, Harshita, for the introduction. I welcome all of you to the 6th edition of Energy Day. Energy Day is a coveted research showcasing and industry networking event of the Department of Energy Science and Engineering at the Indian Institute of Technology, Bombay. The Department of Energy Science and Engineering at IIT Bombay is a unique blend of science and engineering and is one of the few such departments in the country. We are ranked as the top energy engineering department in India, equipped with cutting-edge research facilities, driving innovations in multiple sectors of the field of energy. In the last 3 years, the department has secured 16 plus patents and amassed 110 plus. Energy Day is an opportunity for energy sector stakeholders to learn about the state-of-the-art research and development related to energy systems being undertaken by the department. Energy Day aimed at building a better connection between the department and industry by showcasing the research carried out in the department. We have some great sessions lined up diving deep into the different aspects of the energy sector and covering topics relevant to the current energy scenario. We hope that all of you have an enjoyable experience and leave with a deeper insight into the research that is conducted in the field of energy. Thank you.
Thank you, Rikin, for such a nice introduction. Now, with much honor, I would like to welcome Professor Subhashish Chaudhary, Director of IIT Bombay, and I request him to share few words and welcome our chief guest for today's session, Mr. Anil Sardana. Over to you, sir.
Thank you, Harshita. Mr. Anil Sardana, Professor Rangan Banerjee, Professor Jakir, other colleagues from the Energy Science and Engineering Department, our distinguished delegates from the industry, as well as our young students who would be, many of them will be graduating now in this particular year. I think it's one of the great opportunities that we are able to connect on this very specific program, okay? Even though we are not able to meet personally, but using this platform to showcase certain things that goes on in our department, particularly in this case, the Energy Science and Engineering Department. As you know that those who are from the industry, it is one of our cherished goal that there should not be a gap between industry and academia. And we try our best, no matter how it is, to bridge the gap. And this is one such specific opportunity that we have created, where actually our torchbearers are our students here. Because many of the things that you will be seeing today are the efforts of our students who have done projects. And I think this particular year, they deserve a special applaud from all of you, because it's been very, very hard and distressing year. Is have most of them are not even in the campus, wherever they are, and some of them have difficulty in terms of keeping up with this difficult times in India. But nonetheless, they have come forward. Whatever was possible, which was difficulty that was challenged to them, they have made use of it and have come up with the closure of their projects in many of them. And many of them are highly enthusiastic that their effort should actually see the light of the day. So I'm very thankful to all our students that despite the difficulty, they have put in such a great effort. And we at the faculty, as well as the administrations here, would be very keen to see that these students actually can take up all the challenges, particularly in the energy scenario that the country has to offer. It's a great honor for us to have Mr. Anil Sardana with us today. And India, probably when you talk about energy, anything to do with that, I think he doesn't need any kind of introduction. But being the chief guest, it's also my pleasure to introduce him to all of you, as well as to welcome him on this platform. He has been at the helm of about 6 different companies, and presently holds the position of Managing Director and CEO of Adani Transmission Limited. He is also the Managing Director of Adani Power Limited. He has been in key leadership positions of organizations like Tata Power and NTPC, and has over 35 years of solid experience in this particular field. Mr. Sardana received an undergraduate degree in electrical engineering from Delhi College of Engineering. A warm welcome to Mr. Sardana from our side. We are really thankful to you, Mr. Sardana. Would have much liked to have you visit us, but probably we'll keep it, give a rain check for that for you, so that you do visit us sometime when situation improves. But today, I think I should not be talking anymore, because it's the day of the students, as well as the people from industry, and we would like them to collaborate to each other. And with that, I would request Mr. Sardana to share his views with all our students. Thank you so much.
Thank you, Professor Chaudhary. My greetings to all the students present, as also to Professor Banerjee, Professor Zakir. It's indeed a matter of pride that IIT Bombay, with being at the position at which it is today, is further promoting the industry academic interface. And I think the importance of that can't be undermined at any given point of time. So therefore, compliments to all the students, the industry people for participating in the array of subjects that I saw lined up for the day. In fact, these are very apt, very important. And I must say, while the country is facing very challenging times, as Professor Chaudhary said, and our heart goes out to all those who are harmed or have suffered, including about some of the students which are going through some of the hardship. We hope, Almighty would be kind to bless people, that they stay. But coming back to the life as it must be cherished, and we must try and see as to how one of the key inputs for the quality of life imperative, which is energy, how do we bring that to the masses, to the community? And I think students of IIT Bombay must try and evolve solutions which are more akin to being Indian solutions, rather than for us to, generally swim along with what solutions we see evolving internationally. And you take, for example, we all talk about electric vehicle, we all talk about storage, and these are subjects which are there in every lip at this stage. And when you talk about energy, you certainly talk about those subjects. But see how India hasn't chosen to that option. And I will come to that in a few moments, because I see those topics being covered. And I would urge, one of the reasons it doesn't happen in the same way in India is because we tend to copy, we tend to replicate what's worked internationally. We don't realize our entire system, our morality, our way of looking at things is very different. And therefore, it is very, very critical for the students, especially the brighter lot that the IIT produces, for them to evolve solutions which will work in Indian context. And therefore, as we talk about transformation and we talk about transition, these are some of the words that are part of the jargons that most of us love using these days, because transition more from the fact that we want to land up into a benign format of energy, and transformation because it's going to be very fascinating times. We are all in the cusp of times when no one would have seen technology interfacing as it has never done before. I mean, imagine when would the word be talking about so much of sensorization, IoT, virtual reality, data analytics, robotics, and artificial intelligence. When all of these things are converging, and we are kind of finding use cases for each one of them, these are obviously fascinating times. And you are the people who are going to lend this wisdom to the industry and the community at large. And therefore, it is important for you to use all the wisdom that your professors and your ecosystem has imparted to bring it to industry. But when I say this, I say it with responsibility that we look forward to Indianizing them. We look forward to molding them to, and therefore the learning and the solution versus the global practices must be critically evaluated and analyzed. And we must therefore look at it from that point of view. And when I say this, I'm going to give you a few examples so that it can help you kind of embrace this, internalize this, and also see how do we try and work this out. India, as we know, has adapted to renewable energy. It's nothing great that I'm trying to unfold before you. And we have very fancy targets in terms of 175 gigawatt by 2022, 2, and then we have 450 gigawatt number that our premier gave in some of the forums by 2030. All of these are laudable numbers, great pursuits for us to have. But imagine these REs will all be put either in the arid lands or in coastal areas or in areas which are suitable for either the radiance and insulation for solar or for wind velocities that will be able to convert this into a good RE, viable RE. Now, when we do that, we are trying to take large trunks of corridors from there to consumptive areas. And when we do that, you will be surprised our prices for putting those corridors is going to yield into numbers which are absolutely ill affordable by the community which is going to consume REs. The numbers could be way above 1 rupee 50 paisa per unit, considering the load factor that you're going to see in these genetic sources. So now I'm coming to the moot point. So when the wisdom has to dawn on us to say, how do we really indigenize our solution? You have to also see that it is thwarting some of our existing resources in terms of thermal, gas, hydro, and other formats. And therefore, what we have to see is to how do we blend the two together at the point of injection or nearby, so that we can bring small radial lines to pooling stations where thermal or hydro or the gas or whatever is surplus or whatever is existential should be pooled with RE, and both RE, when I'm saying, I'm conscious of talking about how do we even blend solar and wind and create a round-the-clock solution so that the cost of delivering electrons from the generating point to the point when it is consumed is optimized and not to be seen in the way that people see as they could afford perhaps in Germany in putting offshore wind or Europe trying to do in Scandinavian countries and trying to bring all of that through large corridors, but they can afford those. They pay prices which are 3 times, 4 times our tariff. In India, the tariff elasticity is so poor, you increase it by 5 paisa and people come on the streets. So I think it is these kind of examples that I wanted to suggest that you need to internalize to Indian context, not to the context that exists in Europe or has worked in America or has worked in Australia. Little realizing the fact that in Australia, a consumer will pay 34 cents tariff. And in India, you go anything above 4 cents and you will have the people, ridiculing the policymakers. So those are the examples. Similarly, if you look at the EV, why it's not working in India? Because in India, the morality of putting the battery on a leasing model doesn't work. The guy will tomorrow further sell it, and it will be very difficult for us to locate those guys. I mean, while the battery can be located through various embedded means, but you can't locate the guys. I used to sell during my Tata time telecom solutions along with handsets, and people will de-link handsets with the airtime, and it'll be difficult to locate those guys. And that's why that model never worked, which works in AT&T or which works in Optus or Telstra. So we evolved Indian solutions in telecom. Why can't we evolve solutions in India in the energy side, which can make the EV system work? We have lost that 3,000 cycles of advantage for storage because they are shifting from EV to storage, because after 3,000 cycles, you can harness another 2,000 cycles in the storage capacity because the battery has still a longer life. We have lost that cycle. We have lost that entire advantage. And therefore, perhaps we'll have to go the costlier way of having storage separately and EV separately. So bad because we did not evolve the right solutions for India. So the models in India, I'm re-emphasizing, everything that you talk about needs industry to get the wisdom of these bright, brilliant students to say it's not necessary that what's worked in developed economies will also work in our economies. We need to be proud of developing our own solution, and we need to be proud of seeing as to how we do these things differently. Coming to the similar stuff in terms of benign conversion of coal, whether it comes to, carbon sequestration, carbon capture, carbon utilization, all of that, again, we have not evolved Indian solutions. We have tried to, bring those European solutions and juxtapose into Indian situation. Nobody is going to pay you incremental cost for carbon capture. And how do we therefore make it benign? It's all the wisdom that we need from solutions. Industry is working, but it'll more than welcome. I would welcome some of the energy solutions if they reach out to me and say they want to co-create and create solutions. We'll be more than happy to do so with IIT as well as the students. I want to close by adding the last bit to what I started with, that these are very fascinating times for energy students. Why? Because one, as I said, we are so blessed to have the entire technology paradigm amidst for us to create use cases and for us to integrate that to our existential stuff. That's one big advantage of our times. The second time, which is what I see, that we will soon have electricity being sold as telecom. Let me unfold what my hypothesis is. I am working right now on an experiment where, according to me, every customer will be able to buy electricity through a day ahead or a term ahead choice from any source that it wishes to buy that electricity. You would have the choice of having that on your mobile or you're on the web system. You will connect a customer meter directly to the generator through the middleware, which will become a fixed entity, a complete passive entity, which automatically will have a fixed price from point of injection to the point of withdrawal. So no great rocket science in that. But I will send you an OTP, which you will put as a PIN number on your meter, and your automatic billing will start from a particular generator or a particular package that you'll buy. So like the way you buy today SMS pack or airtime or STD pack or an international pack or a combination or a data pack, you will be able to buy hydropower, gas power, time of the day power. You want to run a washing machine in the night and you want to draw, the entire university wants to draw power in the night time, you will have a different pack. That's my dream. And I'm saying, Professor Chaudhary said, I'm 35 years, no, I'm 41-year veteran of the industry. I passed out in 1980 and I've spent good times and I've had my very enjoyable stints at different locations trying to build institutions. I'm now looking for working with the young wisdom providers to see how do we connect and give this last mile play of reforming, not in a very, kind of conventional and rudimentary way, but in a very modern way of providing the choice to the customer to choose its generator and to create entire middleware as a dumb, passive system, which will just deliver electrons like the way the spectrum does, or like the way the tower ecosystem does that in telecom. And if some of you want to do this project, most welcome to join me. I'm doing that in Mundra area, where I am putting the meters in the colony and taking some of the Mundra units as different stations and program managing that. And that's what my cherished dream is, that this is what are the fascinating times that one will see. So friends, you are in times where the pandemic can be left behind with a positivity of the fact that the quality of life imperatives will change the energy paradigm. Today, we all know that 18 to 19% is electricity. The balance energy is 81% in terms of molecules. We all know there is a prediction that by 2030, we will have 50-50 of that, 50% molecules and 50% of electricity. Therefore, 50% of electricity, how do we really let that be competitive and how do we provide that? And in 50% of the molecules, a large segment will be hydrogen, which is again a new fascinating area that's evolving. There, what will play is not the conventional wisdom of hydrogen, but what will play is how the electrolyzer prices will be brought down. And I am looking at the option, because we also do city gas distribution, as to how do we provide decentralized electrolyzers and put green hydrogen molecules into pipes so that we can actually provide a blended option at a very low cost to customers and evolve more and more of that play. And how do we use hydrogen derivatives in not just the industry part, but also displace 30% of the coal in power stations? And how do we create steam at 600 to 700 degrees centigrade using the hydrogen, which can displace all the ash handling and the coal handling systems that we today have in play at the coal handling plant? So a lot of fascinating technology at play. And what I miss is your company, your wisdom, and your foreplay. So welcome to the industry. And I would look forward to all of you participate. And not only that, I would offer both Professor Chaudhary and my friend, Professor Banerjee, for the other students which are there with them for different other batches, which are still not going to move out of their academics into either higher academics or the industry, to come and work with some of us. And we will love their company to harness and cherish these times, which with the current generation has placed us and blessed us to deal with. Thank you so much, and my best wishes to all of you. And may God save us all from any harm from this pandemic. Stay safe, stay healthy. Thank you.
Thank you so much, sir, for sharing your thoughts with us. Your presence and words of wisdom and the many fascinating ideas which you gave are really a source of encouragement for all of us. We wish our gratitude to you for being with us on this event. Now I would like to welcome Professor Rangan Banerjee, Head of the Department, to say a few words about the department and the Energy Day 2021.
Thank you. So it was a pleasure to hear Mr. Sardana, and thank Mr. Sardana, Professor Chaudhary. Typically in this Energy Day, normally we've been having it in a live session. We usually have a presentation related to the department. Since in the absence of time, I think I will skip the presentation, but I'll just like to talk about three things. First is I'd like to build on some of the ideas which Mr. Sardana mentioned about the context that we are in. And last year was the first year when we did not have Energy Day. We were planning to have it in a live mode, but because of the pandemic, we had to cancel it. And this year we have adapted and gone online. The pandemic has shown us, and the response to the pandemic has shown us a number of things which I think are lessons for us in the energy and the climate sector. So the first thing is we have seen that what is the cost of an abrupt transition. We have also seen how it affects different sectors of population differently, and then that can create havoc in people's lives. We have also seen the fact that we can change our behavior. And these are some things, these are lessons we are seeing today also, the change in the transport, the change in the kind of energy use patterns. When we think in terms of the problems and the transitions that are coming in with climate, some of these lessons are things that we want to avoid. We want to make sure that as we make the energy transition, when we go for a sustainable energy future, we would like it to be a just transition. We would like it to be a transition where we have technologies that are relevant for the Indian context, and yet it is something which people can afford. And this is, of course, a real challenge. We talk about 175 gigawatt or 450 gigawatts, and you will see that most of it is coming in centralized locations in some states. There are others where the economy is completely dependent on coal and coal-based power. And how do you try to make this where you blend it? How do you make it where you have distributed systems and yet make them affordable? We are talking about the hydrogen mission, which is going to be launched later this year. We are talking of electric vehicles. So it's very clear that the energy systems of the future are going to be operated in a different way. The rules of the game are going to be different. And this is both a challenge and opportunity for our students. This is something that IIT Bombay recognized quite some time back. And in 2007, IIT Bombay was the first IIT to actually start a dedicated department of energy science and engineering. We started a number of new programs, a dual degree BTech MTech program, a dual degree MSc PhD program. And I'm happy to inform you that many of the other IITs are now following suit. In the last year, IIT Kanpur has created a Department of Energy Science. And I was told that the Senate last week in IIT Delhi has approved the conversion of their Center for Energy Studies into a department, and they are starting a new BTech program. IIT Roorkee a couple of years back. So I think we must be doing something right if others are also following us. And I hope that the students that we train both in science and engineering are actually going to play a major role in shaping this transition in the future. We have been also involved in actually engaging with the real world. We have a number of centers of excellence that we work with in collaboration with the other departments. With the electrical engineering, we have the National Center for Photovoltaic Research and Education. With the chemical engineering and with other engineering departments, and we have the Center for Oil and Gas and Energy, and this is unique because it has all the 7 PSUs as a part of this center. We have a energy storage platform on hydrogen storage supported by DST with several of the other IITs involved in it. We are host of the Indo-UK Virtual Center. We have also with the TU Munich and with Sitara and the Sign, we have created, we are part of the TU Munich Seed Initiative, which is Sustainable Energies, Entrepreneurship and Development. And as a part of that, we are creating living labs in rural areas. We are working with, in Pabal with Vigyan Ashram, as well as with Gram Urja, to create in a rural context a living lab where one can innovate and look at sustainable energy solutions. We are working with BP where we are looking at low carbon industry options. We are now engaging with Niti Aayog both in order to modify and update their energy planning tool, and also as part of a group of institutions across the country looking at an India Energy Modeling Forum. We also have several student initiatives which are also partnered in by our department students. Our Team Shunya, which is the student team for sustainable housing, won the second prize in the recently concluded US Solar Decathlon in the design for attached housing. Um, Now let me come to the concept of Energy Day. We believe that what we do in terms of our research and work should actually help society. And this is where we started with the Energy Day, way back when we, even before we became a department. And the idea was that all the graduating students would present their research work, very brief presentations. They would get feedback from the industry. This would also help them also tune in, use that feedback, improve their work. Hopefully some of this will be picked up by the industry. And this is to look at relevance. And I would like to just give you, Mr. Sardana is here, I would like to talk about two initiatives to where we are looking at industry and academia interactions. We had long back when the Adani Power was earlier BSES, we had we had 3 master's students from BSES who were sponsored, and each of them was working on one part of a problem. Together, these 3 master's students build up a simulation for the turbine governing system of the Dahanu power plant. So I remember making several trips to Dahanu, and the interesting thing was we had got funding from this from international energy initiative so that we could have sponsored people coming in from the power sector. So this was an interesting thing. The other thing I would like to mention is in our first year we have a department introductory course, and I remember I had written to Mr. Sardana. We wanted the first year students to go and visit the plant, and we went. We saw the control room. We went to the turbine thing. We went right up to the on the boiler control where you can see the entire city. That actually transforms when you see how the challenges when you run this kind of power plant. It gives us a sense of relevance, and I think it's very important for us to try and see how we can engage and encourage and enthuse students, and this can happen only where we have a deep and continuing link with industry. We as a department are planning to start a Master of a MEng program for the industry, and this is something which hopefully by 2022 we shall start. And so just this was just to give you a sort of quick overview of our department and of the Energy Day. I hope that these we have, I think, a little more than 60 presentations in parallel sessions. I hope this interaction will be the beginning of a more enhanced and continued interaction between IIT Bombay and the industry. And I'd like to once again thank Mr. Sardana and Professor Chaudhary for being on this inaugural function. Back to you, Harshita.
Thank you so much, sir, for such a nice overview of the department and Energy Day 2021. I would like to thank again Professor Subhashish Chaudhary for his welcome address, Mr. Anil Sardana for his words of motivation, and Professor Rangan Banerjee for introducing all of us to the department and Energy Day 2021. So before going ahead with the event, I would like to give a few instructions to all the participants and our audience. So there are 4 breakout channels after the general session, having different themes assigned to each channel. In each breakout channel, there will be 2 judges. One is the faculty chairperson and the other one is the industry guest. Channel 1 has a theme named Greenhouse, in which presenters will talk about electrochemical energy storage and conversion technologies. Channel 2 has a theme named Golden Rays, in which presenters will talk about solar photovoltaic and thermal technologies. Channel 3 has a theme named PowerPoint, related to the electrical systems. Channel 4 has a theme named Sustainable Solutions, in which presenters will talk about modeling aspects of various energy systems. Each channel will have 6 to 7 presenters. Each presentation will be of maximum 5 minutes, followed by 5 minutes Q&A session after each presentation. After completing all the presentations and Q&A session, our industry personnel will share his or her experience and interact with the audience. After completion of one parallel session in this way, we will have a small tea break for 10 minutes, and then we will again start the next parallel session with the same instructions. Finally, at the end, we will have a small interactive session with our department alumni, followed by the prize distribution and note of thanks by the overall coordinators of Energy Day 2021. Now I request our industry guests here to join any of the breakout channels of their choice of interest. And I also request all the presenters to stay till the last, as we have many exciting prizes waiting for you. Thank you. To
Hello, how did I come here? I joined some other meeting, right? Professor Banerjee was talking.
Yeah, so this is the breakout room.
Okay.
Yeah. So let us wait for a few minutes till everyone is assigned, and then we'll start.
Hey, Kuldeep, how are you? You're on mute.
Sir, good afternoon, sir. I'm fine working with railways, sir. These are difficult times and we are working, sir.
So, how are things at home?
We are working from home and going to office also, sir.
Okay, both, huh? Okay.
Thank you.
Good to see you after a long time.
Sir, thank you. Sir.
It's been 2 years now?
Yes, 2 years now, sir. Yes, sir. I'm looking after these local trains maintenance in different sheds here in Mumbai, sir.
Okay, so but where is your office?
Trains.
Where is your office?
Churchgate, sir. Churchgate.
So let pandemic settle. We'll meet once.
Yes, sir. Sir, I'll come and visit you, sir.
Yeah.
So yes.
Okay, so I think we should start now. Very good afternoon to everyone present here. It gives me immense pleasure to extend my warm welcome to everyone on the behalf of Department of Energy Science and Engineering, IIT Bombay. I am Arya and I'll be a host for the channel PowerPoint. All of us being electrical and wind energy systems enthusiasts, let us walk through the amazing findings of our research scholars together. Firstly, I'd like to introduce you all to our chairperson. So the faculty chairperson is our very own Professor Pawan Hari. And we also have with us Professor Surya Narayan Dholla. As an industrial chairperson, we had Mr. Dinesh Kumar, but he could not join us today because of some reasons. So before we start, let me share my screen. I hope it is visible. So yeah, these are the few general instructions that I'd like to give you all, that each presentations would be about 6 minutes long and it will be followed by a small Q&A session. I request you all, please do not unmute yourself during the presentation because it may lead to unnecessary disturbances. During the Q&A session, you can raise your hands and ask question to the presenter. I have already shared the Google form link with the jury so that they can evaluate the presentation once it's completed. And if someone wishes to attend some other presentation from a different channel, the instructions have already been given. They can do so using the breakout room option. So without any further delay, let us start the event. So our first presentee would be Pushkar Saraf. Govind, can you please share the video?
So Arya, I think audio is actually not coming. Maybe Pushkar is on mute. It's a.
Yeah, Govind, can you hear me? Hello?
Yes.
The audio is not coming, so please share it again.
Hello, my name is Pushkar. I am a fifth year dual degree student, and my thesis is focused on active power decoupling in single phase power conversion systems. I'm working under the guidance of Pawan Hari sir. So, moving on to the overview. First, we are going to have an introduction, then I'm going to talk about my research. So, what is active power decoupling? Active power in single phase converters, there's usually DC to AC power transfer or AC to DC power transfer. In the case of AC, the power has an average component and a sinusoidal component. So the power supplied from the DC side also needs to have a sinusoidal component. If we don't have an energy buffer, then the sinusoidal component power also is provided by the DC source, which leads to a lot of disadvantages. In order to avoid that, usually we have a capacitor that provides the sinusoidal power. But the capacitor turns out to be very bulky, and it also is a bottleneck for reliability. So instead of that, research is ongoing to try to replace it with a switch capacitor inductor network, where the high frequency will allow us to reduce the capacitor size, which will make it more reliable and also reduce the volume of the converter. So one such topology is of active power decoupling is the bidirectional DC-DC converter. It is the one of the simplest topologies because it only has two switches, one capacitor and an inductor. Even though a lot of research has been done on this, it has always been focused on the control aspect of it. But here we decided to look at the design aspect of it. So if you look at this inverter, it has a high frequency capacitance and a bidirectional DC to DC converter. So basically, if using Kirchhoff's current law, you can see that the inverter current is a combination of these three. Equation number 2. So if the high frequency capacitor provides the high frequency current and the sinusoidal component of the current is provided by the BDC APD circuit, then only the DC value will have to be provided by the DC source, which is the exact thing that we want. So this work was started out by Varun, one of the seniors in my lab. He figured out a design that could be used, a design methodology that could be used to design the BDC APD circuit. Apart from that, he looked at the control aspect of it, which consisted of two loop control structures. So moving to the work that was done by me, I first decided to look at the high frequency capacitor. In order to actually derive and design the high frequency capacitance, we need to look at the current flowing through the capacitor in a carrier cycle of the inverter. Once we look at this diagram, which is this diagram, we are able to derive the equation for high frequency capacitor. Similarly, we decided to look at a simplified BDC APD circuit. This is the average model of the BDC APD circuit, which we used to derive the design equations 8, 9, 10, 11. Based on these design equations, I proposed a design flowchart for the BDC APD circuit. Using this design equations that we have derived, we simulated a H-bridge inverter with the BDC APD circuit in order to verify our design. These simulation results basically verify our design and prove that it is extremely accurate. Moving to the next theme of our research, we decided to look at a more complicated circuit, which is a UPS, online uninterrupted power supply system. It doesn't even consist of a single power conversion system, but two power conversion systems. One is a DC to AC conversion system, that is the inverter, and the other is the AC to DC, which is the power factor correction circuit. The DC link in between will have to handle the sinusoidal current, so it will require a high DC link capacitance, or it will require an active power decoupler. So we first analyze the circuit to look at the double frequency harmonic current, which can be seen in equation 15. It is interesting to observe that this equation has another variable, that is the angle between the output voltage and the input voltage, which was not the case in the inverter. So we also need to control the angle to minimize the double harmonic current. After we minimize the double harmonic current using control based power decoupling, we can then use the active power decoupler to compensate for that current. We decided to look at two topologies for an online UPS system. One is the bidirectional DC to DC converter topology, and the other is the ripple port type topology. The ripple port type topology uses the following design equations. to design the topology. So, based on the design equations, we again decided to simulate the 1 kVA online UPS system, and we verified it using the simulation results. The next part of our research was to experimentally verify our simulation results. That's why I decided to start out with the functional testing of an inverter that was designed by our lab. So basically, the second, third, and fourth picture are that of our inverter completely assembled. The first picture is us trying to test it. As you can see in the oscilloscope, we are giving it signals, switching signals for its operation. It's still in progress and has not been completed. I also decided to design the active power decoupling circuit and the power factor correction circuit. Here is a schematic, completed schematic of the power factor correction circuit, which we have now given to the given so that we can get a PCB of the power factor correction circuit. So these are the references that I've used for this PowerPoint presentation. I would also like to highlight that based on our simulation results and our design, we submitted a paper in Texas Power and Energy Conference, TPEC. Our paper was not only accepted, but our paper won the second paper prize award at the conference. Thank you.
Okay, so we now open the session for Q&A. We also request the juries to evaluate the presentation. Are there any questions? You can either speak up or put it in the chat.
We can move on to the next presentation if there are no questions.
Okay, sure. So next online is Abhishek Sisodia, and the topic of his presentation is synchronous reluctance motor for light electric vehicle. Govind, please share your screen.
Hello everyone, this is Abhishek Sisodia, final year dual degree student from Department of Energy Science and Engineering Department. My project topic is synchronous reluctance motor for light electric vehicle. Here light electric vehicle I mean two-wheeler under the guidance of Professor Pawan Kumar Hari. So this is the table of content. First we will see the overview of the synchronous reluctance motor, then the principle, and down the line we will see design specification and results. So now introducing the synchronous reluctance motor. So the history of the synchronous reluctance motor started way back since 1888. Earlier, this motor was in a very primitive form of its development, and it wasn't good at its performance. So down the line, with the modification in the technologies and the development that are happening in the manufacturing industries, this type of steam motor is now commercial, but it's not commercial yet in the field of electric vehicles. So correspondingly, you can see till 1998, it has reached to the significant modification from its very primitive structure. So now understanding the working principles, whenever a paramagnetic material is placed in a magnetic field, it experiences a force, and that force is called reluctance force. As we can see in this image, the paramagnetic material tends itself to align along the field lines, so making itself in the minimum reluctance position. Similar is the concept with our rotor, since this is the direct axis where this bars are pointing, and the one that is here, these are the barriers that are there in the rotor structure. So this is the q axis, as we can see correspondingly in the bar of the ferromagnet. So it will try to align the rotor in the d direction, and that will have the maximum flux, and the q direction will have the minimum flux. So this traveling of flux in the direct axis and quarter axis, this is the ratio of the flux traveling in the direct axis and the ratio of the flux that is traveling in the quadrature axis is proportional to the direct axis ratio of the direct axis inductance and the quadrature axis inductance. So this is, we can say, this is what we call salience ratio, and correspondingly the power factor can be determined corresponding to the value of the saliency ratio. So the project objective was to design an efficient drive which provides high starting torque, robust in nature, economically feasible, and low torque ripple, regenerative braking, and low noise. So these were the objectives. So the synchronous reluctance motor is the one that fits the most suitable for the objectives that were defined earlier. So since it is a AC rotating field machine, and the possibility of extremely smooth torque and good operation at low speeds, and the rotor has a salient point and no windings are there, and losses will be minimum since there is no windings on the rotor, and rotor can be constructed entirely from the high strength material and low cost material, since the reluctant synchronous motors were expensive because of the neodymium magnet that are there, but since we are getting the same synchronism in the synchronous reluctance motor and at the lower cost of the higher output facility. So as you can see, the starting torque of the synchronous reluctance motor is somewhere around 300 to 350% of this its rated output torque, and till 200% of its rated torque it doesn't loses its synchronism. So coming to the design specifications, the output specifications that we have desired based on the calculations we have done for the real life problem. So the torque that is required is 60 Newton meter, and we have desired the speed of 60 kilometer per hour, and the corresponding angular speed for that speed is 520 RPM. So this torque and the angular speed we have gives the power output that is required. So based on these output variables, we have calculated our input, and I would like to mention that voltage here it is kept 100 volts, in keeping the safety of the personnel into the consideration, and it is a three-phase motor. So based on these output and input values, we have designed a motor whose structural specifications are mentioned as above. The stator outer radius is close to 294 mm, and the air gap I would like to mention is 0.3 mm. The number of slots in the slot in the stator are 36, and the number of poles are 4. So this is the design synchronous reluctance material, and the simulations were done on the ANSYS. So this is the simulation picture of the design prototype. So this is the cross-sectional view of the same, and this is the cross-sectional view with the two-layer winding. So now the results, since I have mentioned that the performance of the synchronous reluctance motor depends on its saliency. So saliency is nothing but the ratio of the direct axis inductance and the quadrature axis induction. So as we can see, the average value is coming around 0.78, and the average value for the q-axis is coming around 0.8. So the saliency ratio that we are getting is somewhat near 8.5. So corresponding to that, our power factor is coming to be 0.78, which is good. So the torque that we have desired is 60 Newton meter, but the output torque that we are getting after the simulation is more than that, which is good sign for us. Ripples are there in the torque, but that would be minimized after the further modifications in the design. So these are the input voltages that we have, since I have mentioned keeping the safety personnel into the consideration, it is 100 volts. So as we can see from the graph, it is not going beyond the 100 volts. So this is a stator current. So stator current As you can see, the phase currents of all the stator windings. Thank you.
Okay, so let us open the session for Q&A. Are there any questions you can ask him? Also, please, the chairperson, can you evaluate his presentation?
Surya. Professor Surya.
Yes, Paul.
Yeah. So do you like to ask the candidate any questions?
No, I don't have any specific question. No.
Okay. Okay. Yeah. Thank you.
Okay, so
Then I think
we go with
yeah.
our next candidate, and it will be Trishant Roy. So I'll be sharing my screen.
Am I audible?
Yes, Trishant, you are. Just a second. Is it visible?
Yeah.
Okay, so you can start.
Yeah. Can you do the presentation now? Yeah. Good afternoon, everyone. My name is Trishant Roy, and like my thesis topic is power sharing in hybrid AC/DC microgrids. So the goal of this thesis is to formulate decentralized controllers for optimal dispatch of distributed generators while ensuring proportional power sharing for islanded hybrid AC/DC microgrids. So, like by definition, a microgrid is an independent low or medium voltage distribution network consisting of various DGs, generators, energy storages, and various loads. The advantage of using a hybrid microgrid over AC microgrids is that we can use AC as well as DC sources and loads in hybrid microgrids. Microgrids are especially useful in places where like connection to grid is difficult or is intermittent. In this thesis, we are trying to tackle one of the main operational issues in hybrid microgrids, that is power sharing. Uh, so, um, so the steps, like the goals of the thesis can be divided into two parts. The first part is to develop a centralized optimization strategy to optimally dispatch uh, uh, power among the various components. In the second part, our goal is to try to extract decentralized models from these centralized optimization data in order to mimic the optimal performance given by like when we know all the parameters, but in real time we do not use like through decentralized control. So the issue of power sharing is due to the use of group control in the generators we have. So in the image, we can see that there's a 6-bus hybrid microgrid with 2 DGs and one load on each side. Uh, so in conventional group control, uh, voltage and power are related, and voltage and reactive power are related, and frequency and active power are related. So when we use these equations, there's no issue of real power sharing because omega n and omega s are same for all the nodes. But that is not the case for voltage. Since Vs is different for different buses, then Vn minus Vs will be different for all the buses. And in turn, this will result in NQ into Q terms not being equal for the various DGs. Why NQ into Q is important, being equal is important, uh, is that the value of NQ, that is the droop coefficient, is inversely proportional to the rating of the generators, the size of the generators. So we expect that the smaller generator should give like equally proportional smaller power. So uh, in our algorithm, our goal is to optimally choose the value of Vn such that we are able to achieve NQ into Q equal for all the DGs. The same is the case for DC microgrid, where NP into P, like we are trying to achieve equal NP into P values. Yeah. So in this thesis, we are trying to uh, develop decentralized control. Like why decentralized control is important is because like when we use centralized control, that is when we use all the information of the network, we know how how all the other DGs are operating. Like to implement this, there's a need of a communication infrastructure which will be economically costlier, and also it will be vulnerable to any kind of disturbance. It may be faults, or it may be like purposeful attacks. uh, so in our thesis, we are trying to develop we are trying to use learning based techniques to develop these decentralized models. Learning based, like the motivation of choosing learning based models uh, is that like since a microgrid is a complex system, and we cannot like conventionally derive uh, the relations uh, the optimal relations between Vn and the various local variables, we try to use learning based techniques here. So coming to the first part, the formulation of the centralized optimization strategy. Here we are assuming that we know all the network parameters, the various ratings of the components, and the load profile. We try to pass it through an objective function which consists of minimizing power loss and power sharing error. By power sharing error, I mean that we are trying to minimize uh, the delta QS and the delta PS terms. So if we try to like minimize those, like the minimum value of them will be zero, delta QS and delta PS. And if that is the case, then N into Q and N into Q, N1 Q1 and N2 Q2 will be equal. And the output of this formulation will be the dispatch schedule, which will be the power uh, that the DGs and the interlinking converter should like provide. The second part is the extracting a decentralized model. So for this, like a test system that we took was a 18 bus system which had 5 loads. So what we do is that for each of the 5 loads, we keep 5 states, which is 20%, 40, 60, 80, and 100. And like permuting all these cases, we get 5 raised to 5, 3125 cases. From there, and we run the optimization, like the proposed optimization formulation for all of these cases, and get a relation between, like we get the data points like for all the cases, and then we try to form a relation between Vn and P, like the active power, the real voltage, and the current at each DG, using a regression-based technique. We check whether uh, the model that we have used is giving a good fit to the data, and whether it's underfitting, whether it's not underfitting or overfitting. Then after that, we like run the simulation to check if there are any convergence issues. If all of these checks pass, then we accept the model. So, like here are a few simulation results that we have tested. So first, we took a six-bus system uh, consisting of two DGs and one load on each side, and we like the optimization results. Excuse me, gave that like we are like able to achieve perfect power sharing. So, like in the network that I had chosen, the size of DGs were in the ratio 2:3. Like DG1 is to DG2 is 2:3. So we can observe that like the dispatch schedule, like the suggested dispatch schedule gave the corresponding like ratio. In the DC microgrid size, the DG ratings were in the ratio 1:1, and we see that we are able to achieve perfect power sharing with the proposed algorithm. We simulated this on Simulink on the six bus system, and we see that we are able to like validate the results. So the scope of improvement in the proposed algorithms are that in the first part, in the optimization formulation, like we can improve the modeling part by considering a transformer in the AC side of the interlinking converter. Also, the proposed formulation has many decision variables, and like in order to like linearize V into I products and I square products, so there can be improvements in the modeling part to reduce the number of variables required to do this. And next, in the learning part, we can explore reinforcement learning so that the requirement of the data set is minimized, because like in the current algorithm we would need to uh, run the uh, run the optimization formulation for so many cases. So these are few improvements that can be done on top of this work. uh, Thank you, and let me know if there are any questions.
Do you have any questions? All right, Trishant. So yeah, I think, can you go to slide 7? Page 7. Yeah. So here you have generator 1 and 2 in the right side figure. No, the next one drop. There are two plots in that slide. Can you go to that slide? Here. So generator 1 and 2. So they're supposed to share equally. That's what you intend, right?
Correct. Yeah.
So okay, what could be the reason for this difference in the transient, and can it be also improved? That is one question that I have. Can you also make sure that even transients are kind of fairly good sharing happens even during transients, because now they are actually far apart?
So like we cannot like from the proposed algorithm we cannot ensure that in transients also there will be proportional power sharing, because like the the analysis that we are doing, the optimization part as well as the learning part, we are using only the steady state data. So yeah, like the transient part that is there is uncontrollable, like in this proposed algorithm. Uh,
Because see that in the transient, I think one generator is showing some negative power.
yeah,
That means it is consuming.
correct. Yeah, yeah, that's a good point. Like we need to improve that part.
Yeah,
Yeah,
think about it.
yeah.
Thank you. That is all. Do we have any more questions?
So I have a question, Trishant. So what does actually this negative portion in the blue line indicate? You see a blue color plot on the
Yeah.
right side, right? The proposed algorithm. What does actually negative signify here?
Like the DG will take real power, like the current.
So what is there in the DG there? Is it an inverter or what is it?
Yeah, in this study we are considering inverter-based studies, inverter-based uh, like inverter-based generators. In this study are we are modeling the inverter as a constant voltage source, as a constant voltage source device where like we set the desired voltage is feeded into the the inverter.
Okay, thanks.
I think Hari Krishna has a
Hi.
question.
Yeah, hi. Can you hear me?
Yes, sir.
Yeah, thanks. Nice presentation. I have a couple of questions. I will keep it quickly. In one of the tabular form, the power flow through active power flow through interlinking converter is zero, whereas only reactive power is flowing as the share is increasing. Can you go to the tabular form, please?
Correct. Yeah.
I think next one, if correct. Maybe next one. Sorry. Other tabular form. Slide 6 or something like that.
Yeah, I think there's some delay from my side. Are you? Can you go to that slide? Slide 7.
Yeah, now it's showing page 8. Yeah, here it is. Yeah. 7, page 7. Okay, thanks. So here the interlinking converter, is it acting like a reactive power support? So I can see that as the load level is increasing, only reactive power is increasing. So what I can conclude from this slide, can you please describe?
Yeah, correct. Yeah, the interlinking converter is providing only active power, only reactive power to the AC side. Uh, Basically, this is happening because, we can see, in the formulation, what we are trying to ensure is that we are uh, ensuring power sharing, which we can see from the DG results. Like there's equal power sharing in DC, and then there's 2:3 ratio in the AC side. On top of this, we are trying to minimize the losses in the network, the I square R losses. So, like, because we are using that also in the objective, I think that is the reason why we are getting a solution where the real power through the ILC is zero, and some reactive power is being supplied by the ILC.
Oh, so it is not that the reference for interlinking converter is intentionally made it zero. Is it something like that or what?
No, it's not
Did
purposefully.
you consider that?
Yeah, could you continue?
Yeah, did you consider that the active power flow through interlinking converter is to be zero? Did you consider that condition?
No, there was no I did not constrain it to go to zero. The minimum loss plus minimum power sharing condition resulted in this result. It was not
Okay.
purposefully done.
Okay. Okay. Yeah. Thank you. Thank you very much.
I think just to add to what Prashant has mentioned, I think it's also not a good idea to tell interlinking converter not to supply any reactive power. The idea of interlinking converter is it should just act like a transformer, which will just allow power to flow freely depending on the supply demand gap. In this case, if I remember correctly, the original paper refers to use of a droop control in the interlinking converter. So depending upon the voltage on one side and frequency on the other side, power will actually be moving from left to right and vice versa. So I don't think he has any plans to implement a restricted power flow in this case.
Okay. Okay. Yeah. Thank you. Thank you.
Okay, so let us now move to our next presentation. Next we have Jyoti. Jyoti, are you here?
Yes. Am I audible?
Yes, yes. Just a second. Yeah. Can you control it?
Mm-hmm. I don't know, there's some lag, I guess.
So should I do it or will you like to continue?
Yeah, I'll continue. Good evening, everyone. My name is Jyoti Martolia, and my MTech project is on thermal characterization of silicon carbide MOSFETs under the guidance of Professor Pavan Kumar Hari. So the motivation in the present era, due to increase in power demand, the need for efficient and compact power conversion system is with high volumetric densities is becoming significant. And so the power converter needs to be designed in such a way that the damage due to temperature rise should be minimized, and in order to evacuate this heat generated at the junction, we need to select an efficient heat sink, which further adds to the cost. And wide band gap based power devices like silicon carbide and gallium nitride, they have better thermal characteristics as compared to their silicon counterparts. They can operate at very high frequencies and high temperature. They have high thermal conductivity and low on-state resistances. And the objective is thermal characterization of silicon carbide MOSFETs, which mainly includes thermal modeling, power dissipation calculations, heat sink design, and then the study of thermal parameters. So silicon versus silicon carbide. So as you can see that the critical electric field for silicon carbide is almost 7 times than that of silicon. So it allows the designer to design devices with smaller size and with satisfactory on-state performance. Energy band gap is also 3 times for silicon carbide. So we can design devices which are thermally stable even at very high temperature, and the thermal conductivity is also 3 times for silicon carbide. So for same temperature rise above the ambient at junction, one can design devices with high power densities. So these are the advantages of silicon carbide over silicon. And now comes the thermal modeling. So you can see that this is the DBC structure of a module, and these are the different layers. So the thermal parameters across different layers can be evaluated if we know the physical dimensions of different layers and the physical properties by using these two expressions. So you can see that this is the specific heat capacity. This is volume, and this is thermal resistance and thermal capacitance. So once we have the thermal parameters across different layers, then next we can do is we can convert this physical model to thermal model equivalent. So this is the thermal model equivalent of the system. So here these are the thermal parameters across different layers, and as you can see that these are the functions of temperature. So if we want to increase the accuracy of our evaluations, then we can include these changes in our evaluation. So these two equations are representing the relation between thermal conductivity with temperature and specific heat capacity. Now how does it change with temperature? So yes, once we have the thermal equivalent circuit, so yeah, this is the power dissipation across the junction or switch, we can say. So which is the summation of switching power loss and conduction power loss. So once we have all this data, then we can proceed further. So for evaluations, we took this basic circuit. So these are two N-channel silicon carbide MOSFETs acting complementary to each other, fed by 600-volt DC supply, and this is the we have used one RL load, and depending on the current across the inductor, these ranges have been estimated, and these are the different parameters that we have taken for our evaluations. And yeah, so once we have the power dissipation across the switch, and this A represents the ambient temperature, and this is the thermal equivalent circuit, and this is the sink to ambient thermal resistance. And yeah, after we calculated the power, then the next thing that comes is the heatsink design. So depending on the power dissipation and the temperature rise that we want to restrict at a junction or different points, we can select on an appropriate heatsink. So we can get these values from that heatsink data, and these node voltages at different nodes are equivalent to the temperature. And so by evaluating the temperature, by evaluating the node voltages at different nodes, we can estimate the temperature rise across different points with respect to the ambient. So it has been observed that the temperature rise, first it increases exponentially, and after sometimes it saturates to certain value. So we can calculate the transient time also and the steady state value. So these are the results. So we did the analytical evaluation first and the simulations. So as you can see that the parameter values are not very far from each other, although the slight variation between these two is because of the assumptions that we have taken. For example, we have taken power loss as constant, which is not the case in actual scenario. It changes with temperature, and if we incorporate all these changes in our evaluations, then this differences is likely to reduce. And for the future work, we are analyzing synchronous buck converter and change in electrical and thermal parameters, which will be further validated with our simulation results and experimental results. We will also be analyzing what are the different parameters that depends on temperature, and which of these parameters are most significant, which of the parameters are most significant and affected the most by the temperature change. And we will also be analyzing the heatsink design for individual switches, and we can also the heatsink for a whole system, and which one is more efficient. Thank you.
Questions, please.
Is it okay if I ask a question, Pawan?
Yeah, please.
So thanks, Jyoti, for I think very simple and crisp presentation. So see, in the circuit that you have actually drawn, there are two silicon carbide switches.
Yes,
so
sir.
what is the role of the switch in the bottom part of the leg? Yeah, the IS2. So what is the role of that particular switch here?
Sir, actually, we were using this switch to to check that all the modes of conductions are covered in that. So
so if I try to let's say, so what kind of operation are you doing? You are actually doing this as a buck operation or boost operation?
so actually this one is just the first circuit that we came through. After that, we are implementing all these things into synchronous buck converter. So I'm working on that currently.
So where you will be using only one switch, right?
No, sir. There will be two switches. Synchronous buck. There will be one inductance, capacitance, and load resistance also.
Okay, but how many switches are you using there?
So two switches.
Two switches. So one of the switch may be playing role of a diode most of the time.
Yes, sir. When we are not giving any signal to the lower one, then it will act as a diode. But when both the switches are on, then the current will likely to flow through both the channels. So at that time.
Okay, fine. Okay. So is there any specific reason why you have actually chosen synchronous buck converter?
Sir, I think that is more relevant. Applications. It has got more relevant applications, so that's why.
Okay. Can you just elaborate it a little bit? I could not really follow. More relevant application in what sense?
So I mean that is a more like used circuit in industry and other things.
It's widely used in the industry. Okay.
That's
okay.
right.
Thank you. Thank you very much. Thanks. I'm done, Arya.
Okay, so before continuing, I'd like to welcome Mr. Dinesh Kumar from Havels, India. I couldn't follow when he came. So we welcome you, sir. So I'll stop sharing my screen. So the next presentation is from Kumaris Ramesh. So Govind, can you share your screen?
Am I audible?
Yes, you are.
Yeah, okay, thank you. Govind, you'll be controlling the presentation, right? Uh, or if just yeah, or would it be possible if you could give me control? Let me see. Yeah, okay, cool. Yeah, cool. Thank you so much. Good afternoon, everyone. I'm Kumarish Ramesh, a fifth-year dual degree student from the Department of Energy Science. I'll be talking about transit bus electrification, focusing on impact analysis and transition planning. Uh, so, just, yeah. So in the past few years, studies in the Indian context have shown multiple imperatives, both current as well as future trends, to shift to electric buses, as you can see on the slide. However, the problem is that these studies focus only on comparing the impacts of specific vehicles. So my project focuses on transition trajectories for the entire fleet. The model helps basically understand the trade-offs, both in terms of in terms of time, as well as the environmental as well as economic impacts at different points of time across the transition period. And this model will also help the transport undertaking as well as the fleet operating service to design business models to electrify and operate the fleet within the cost and the carbon budgets. We'll understand what exactly the trade-offs are when we come to the model. Uh, Yeah. So before we go to the model, let's look at the four key transition decisions that characterize the pathways. So while the first and the fourth one are pretty self-explanatory, let's look at the other two. So rate of electrification, right? Even when you're given a specific fleet electrification target, say 100% electrification at the end of transition period, you can do so in different ways. So either you can do it rapid upfront to maximize savings on fuel costs, or you can do it gradually, or you can delay it so that you can exploit the falling battery costs. So this model provides 5 alternatives, each labeled A is to B, that is like from 1 is to 1 to 1 is to 3, as you can see, where they indicate the relative proportions of the fleet of the total electrification that will happen across the transition period. The order of electrification comes into play when your routes are different, right? So uh, you can choose which routes to electrify first. Of course, by prioritizing longer and high capacity routes, you will again save on fuel costs because electricity is cheaper than diesel on a per kilometer basis. Whereas shorter and low capacity buses means that purchasing those buses upfront is cheaper. So now let's move to the model itself. Right. So the first aspect of the model is the drive cycle analysis. So given just the stops and the timings for each route, you do not have any other information. You can input it into the drive cycle generator, the algorithm for which you can see here below. And then that will give you drive cycles. For instance, we have plotted a sample drive cycle for a route for the first hour. Now this drive cycle further is fed into the drive cycle analyzer, giving you certain key drive cycle statistics. Now, these key drive cycle statistics will be used along with the vehicle characteristics, the temperature and loading profile, and the day and month to generate the energy consumption for each day. So on the right hand side below, you can see the integral form of the energy demand equation, which uses the drive cycle statistics, which are highlighted in red color, the vehicle and loading characteristics highlighted in blue color, and the temperature data highlighted in the golden yellow color. So on the left hand side, of course, is the form that most people are generally familiar with. It's the longitudinal dynamic schematic. These are both equivalent, just that this is instantaneous, whereas the right hand side one is the integral energy demand for the entire day. Now, I'll give you a snapshot of what the model really looks like. So it's been built in Excel. So you can basically choose the bus, the route, and the fuel variants, and you will get both the daily energy breakup in terms of where your energy is going, and you'll also get the average values for the entire year. So this is important because different temperatures mean different cooling requirements. So you get an average value for the entire year. So we keep this aside for now, the energy use and emissions. We go to the next part. So this is the transition scenario generator. So basically you input the initial fleet mix and then the four key transition decisions that we talked about. You input it here and then you basically can obtain the transition scenario. So for example, for a 600 bus fleet for the given values, the transition plan looks something like this, where this graph goes from 2023 to 2035. Of course, you also have the data for each route, as in when it's going to get electrified, but I've not shown here because it might be too cumbersome to view it. So we keep this transition plan aside, and then we move to the third aspect, which is the costing module. So you have the five components, that is the electric bus pricing model, the diesel and CNG bus prices, the O&M cost, which is basically fuel and maintenance, the charging infrastructure for electric buses, and the inflation and interest rates. These five put together give the costs model. Uh, and then finally, we come to the business model in terms of how do you want to service the financing? Do you want to, what is the loan that you're taking, and are you purchasing it upfront, and who is operating it, so on and so forth. Now, given these four aspects, we can combine these four to get the results that we want: the yearly fleet mix, energy and fuel consumption, the emissions, as well as the costs. Now, we'll just have a look at a small case study. I hope I'm within time. Uh, so we look at a short case study for a 600 bus fleet, which is initially composed of 90% diesel and the rest CNG. So this bus fleet has been extrapolated from 24 routes for the Ahmedabad BRT system, the line one. We've taken just a conservative estimate for the battery pack price reduction, so that even in this, we can see what the impact of electrification is. The four scenarios we'll be looking at is CNGF, that is complete CNGification, the E50, which is 50% electrification with rate 1:1. And scenario 3 and 4 are basically 100% electrifications with rate 1:2 and 2:1 respectively. Now, we'll just have a look at the total and the fuel costs. So these are the annual costs from 2023 to 2035, which is our transition period. The solid lines give us the total cost, whereas the dotted ones are the fuel costs. So this might be a messy graph to look at first, but a few key takeaways, right? So the single highest investment required in any year is for the complete electrification 2:1. That is the green color graph. It's the only one that goes above 1.6 billion rupees in a year. But also look at the point that this is the only trajectory that actually goes below 1 billion rupees, and that too, it gives these results for 5 consistent years. So in a sense, it's characterized by high upfront investment and significant cost reduction towards the back end, whereas the other three have kind of similar total cost patterns. However, when you look at the fuel cost, it's obvious that it's not really the same. So for instance, the complete electrification 1:2 has high fuel cost upfront because you're electrifying it very slowly, whereas towards the back end, it rapidly decreases, whereas the gap is filled by the capital investment involved in purchasing buses. So this is a very quick snapshot of really looking at how different trajectories can influence the cost differently. Of course, we have taken an outright purchase model, and there are we have not really taken any interest rates and loan servicing. Through loan servicing, of course, you can modify these costs and say you're purchasing the bus, but the costs are distributed across the time period. So you can always do that, and that's the motive of the project, to help transport undertakings as well as the fleet operators to design suitable business models. With that, I would like to thank you for attending the presentation.
Quite energetic presentation. I'd like to request the chairpersons to keep evaluating the sheet. Also, if there are any questions, you can ask.
Yeah, I can ask a question. So, Kumaresh?
Yes, sir.
Okay. So, the scenarios what you have presented. So, what is
Yes.
the cost of electric vehicle or this electric bus you considered?
The electric bus that we have taken is basically we have priced it in the sense that there is a battery pricing and there is a non-battery aspect to it. So currently, if you look at the current cost, the longer bus, that the 12-meter bus, our model takes it around I think 80 lakh, and the 9-meter bus at around 65 lakh, 65 to 70.
So did you consider the same size of bus for CNG as well, or?
The problem that we're actually having is that we don't have a lot of market data. So we have not really sort of taken the same bus size, but what we have taken is a similar bus capacity, and what the cost of it is shown on, like what is kind of the cost of those models.
Okay, so last question from my side. So in addition to cost, what do you think would actually be the barrier to electrify buses by 2035?
The point It would be the charging infrastructure, but so let me explain that. So the electricity demand itself, if you're talking about it, it won't be much. uh, I mean, we could do a back of the hand calculation, but I've seen like papers, and it won't be if you're just looking at electrifying a bus fleet, right? And especially in a big city like Ahmedabad or Mumbai, the demand itself won't be much. But the two aspects is, one is that infrastructure itself should be in place, in the sense that you have all those you have the physical connections, you have the chargers. And second is that electrification, if not done properly, or if not really well planned out, it may lead to disruptions in the service schedules. And if that happens, then there would be pushback from the public, and you would go back to the IC engine.
Thanks, Kumaresh. Arya, I'm
I
done.
have one question. Can I ask?
Yes, sure.
Yeah. So, have you considered while doing the costing and all the running cost, the state of health of the battery will come down with time, and maybe you have to replace the battery after 6 years of operation?
Yes. So, I think, are you talking about the reduction in battery prices, right?
No, I'm not talking. Say today you purchased a electric bus, and you would have calculated the running cost of that thing. So, for example, to run 100 kilometers, you need this units of electricity, for which you need to spend this much,
Yeah.
corresponding to the mileage thing of this. But that thing is valid today, but say down the line 3 years, your battery will start deteriorating, its state of health will come down. So that will change. Or maybe after 6 years of operation, you have to replace the battery because the state of health has come down below 70%. So have you
Yeah.
considered that?
So we have actually not so battery degradation, of course. I'm not sure if the mileage will sort of be affected, but of course the storage capacity of the battery will be affected due to sort of cycles. We have not considered that currently. One of the reasons I did not consider it right now, although it's a thing I've been thinking about, is because we have also considered just the slow charging technology, and the capacity for battery that I've considered, I've slightly oversized it as is done usually in India. So these buses have a capacity of 300 kilowatt hours. So what I'm hoping is that we'll also have fast charging in place. Uh, you know, say 5 to 8 years down the line, and we can afford smaller batteries. Very heuristically, I just said that okay, let's just cancel out each other. But yes, I agree that we should consider both sort of the degradation of battery storage capacity and replacement, as well as any new and better technologies. So I'll surely be doing that going ahead. Thank you.
Okay.
Sir, Anuradha Ganesh, Professor Anuradha Ganesh.
Yeah, Kumaresh, I think, I mean, at the outset, the presentation and the attempt is really very good. Though it is, I would say it is generalized to a large extent but the approach is good. Can you tell me what is it that you are really targeting? Are you targeting the fleet owner, so information for the fleet owner, or a recommendation to the government, prediction based on which the infrastructure development should be recommended? I didn't really get what you are trying to achieve by doing this.
Yeah.
Can you quickly tell me that? Yeah.
Yeah, sure. So when we look at this, cost, right, and I've not incorporated any different kind of business models here. But so, for instance, if you look at the FAME 2 scheme, right? So FAME 2 scheme provides subsidy to say organizations like BST or NMMT only if they follow the gross contracting model, wherein the undertaking doesn't operate it, but someone else does. So when you operate it in that kind of a business model, your costs will change. So what I'm looking to do is one, help these transport undertakings who are also the fleet owners typically, to see, how to sort of design contracts and how to design the bid propose not bid proposals, the call for bids, right? So how do you design these operating schemes so that they can operate, say, within their budget constraints? So if maybe they cannot spend 1.6 billion rupees but they still want to electrify upfront, then how do you shift these costs? What kind of operating business model choices
Right.
do they make?
Right, well said. So you're talking about CNGification. Now, CNGification itself is something which has to be looked at separately. Forget the infrastructure, but whether we are, because there are asks for, I saw some tenders now which is talking about retrofit, or do we want to have new buses with full CNG?
Yeah.
Okay, and then comes electrification. So I'm not very, I would, my recommendation is that maybe you want to just take, you only take electrification and move on and leave the rest to whether it is CNGification or, retrofit or whatever it is. That's one, because it's very confusing like this, and there are just too many parameters. And I also invite you to talk to me separately, and if you need more data and all, I'll be happy to, whatever I can, I would be very happy to give you
Oh,
more
sure.
data.
That's exactly what we want. Like, we're lacking for market data, and like we need to make assumptions and
Whatever we can, I'll ensure that we share it with you.
Thank you so much.
But good, very good attempt, I would say.
Thank you.
Thank you, Kumaresh. Thank you, ma'am.
Thank you.
So
Can I? Yeah, I can go and can stop.
So let us move on with our last presentation of this session. So we have Satya Prajna Sahu. Govind, can you please share the video?
Hello, my name is Satya and my project is parallel operation of microinverters. Let's start.
Satya, sorry.
A microinverter.
You have to share the video. Like, stop sharing the screen and share that one.
Whosoever it is very nice to see Jaya and Amitabh Bachchan and Shah Rukh Khan on the screen.
Yeah, now the screen is visible.
Hello, my name is Satya and my project is parallel operation of microinverters. Let's start. A microinverter is a device that converts the DC power available from a single solar panel and converts it into AC power. So it is essentially a downscaled inverter. Why exactly do we need it over a centralized or string inverter? It is a very compact device. It fits on the back of a panel and lasts for its entire lifetime. It is a very simple device. It's a plug and play device, and you can connect on one side to the panel and the other side the grid or the load that you're supplying. It is very reliable. So the failure of a single module will not affect the power flow of the other modules. It is very modular, it is scalable, and it is very efficient as each inverter runs at MPP. So let's look at some of the microinverters that are available commercially right now. In India, so Crystal Solar Energy, FCHR Solar, Nordic Solutions, and etc. All of these companies provide microinverters. These products that are in the market right now, they are very efficient. They have a very high peak efficiency. They have excellent FPP tracking, grid synchronization, voltage and flexibility, and others. But all of these products in the market, they only operate in the grid connected mode. So they cannot operate in the standalone, or though they have no mode transition control as well. So why exactly is standalone mode important? If you think about it, the electrical grid of the future, it will require a lot of decentralized and distributed generation resources. So a lot of these will be clustered with the local loads and they will form a lot of microgrids. Secondly, a major market for microinverters right now are rural and off-grid generation resources. So in these cases, grid is either intermittent or unavailable. So we need the microinverter to be able to supply power in the standalone mode as well. So what exactly do I mean when I say parallel operation of microinverters? A cluster of microinverters with their local loads connected singularly to the grid is the case that I'm considering here. So multiple parallel units of microinverters, but not multiple independent units connected to the grid. The advantage of this setup is that the power flow to the grid is more controllable and consistent. So the entire cluster can be considered as a constant power load. So to connect anything to the grid, there are certain grid codes, and some of these grid codes are provided over here. So for example, the total harmonic distortion should be 5%. So this is across all of the standards, Indian or outside India. Also for power factor and islanding and PV modules, grounding. So to design a microinverter, we start with a power electronic design based on the performance. After the power electronics design, we model the circuit. So there are a lot of non-linear elements in the circuit, right? So we have to linearize it before we start modeling it. So we linearize the circuit, then we do a state space modeling using small signal approximation. After that, we find the control to output transfer function. So that depends on what controller we are trying to design, whether it is a voltage or a current controller. After we find the transfer functions, we gauge its stability, and then we design compensators for the same. After we design these compensators, then we verify the compensators and our models using the simulations. So on the right, you can see one equivalent relay circuit of the flyback controller over here of my circuit. So my system consisted of a two-stage power conversion. The first stage was a DC to DC voltage boost, which was done using a flyback controller, and the second flyback converter. And the second stage, power conversion stage, was a DC to AC stage, in which I used an H-bridge inverter. So this figure shows the linear circuit of the flyback converter. And this figure shows how I verify my model and my compensators when I derive them. So let's see at some of the results. So this is a Bode plot of the current controller in the inverter system. And this is the verification of the models that I had found of the current controller. So on the left is the simulation that I had done using Plex, and on the right is the transfer function result when I give the same input. And here you can see the stability of the current system when using the compensator and without using the compensator. Okay, so now let's look at some of the control. The control I used was a droop-based auto voltage inner current controller, which is the reason for this is that I want to be able to control the power in both grid connected and standalone mode. So in the grid connected mode, I will just use the current controller over here, and in the standalone mode, I will use the entire control circuit. So now with this controller, I was able to achieve a certain amount of satisfactory transition performance from the grid connected to a standalone case and vice versa. Comparison with the IEEE 1547 standard is seen over here, in which IEEE 1547 is a standard for reconnection of any power generation system to the grid, and it sets a limit for how much clearing time should be there for all of these cases. Thank you.
Questions, please. Hari Krishna,
Hello. Yeah. Can you hear me? Hi.
Yeah, please go ahead.
Hello.
Yes, we
Yeah,
can hear you.
I understood that you've been followed. Yeah, you followed linear analysis model. So how you model? Even you have modeled the every component like a colors as well, and resistance loads also have you modeled in linear analysis?
I'm sorry, could you repeat that question?
Yeah, my question is that you said that you followed a linear analysis model to evaluate the stability. So while modeling the network, like controllers as well, like voltage controller, power controller, current controllers, have we considered as a linear models?
Yeah.
Oh, okay. So you write some differential equation for each controller. So
I'm sorry, I lost you again.
yeah. So my question is that, like, for grid connection and islanded mode, did you find a difference while making the stability? So if the controller is working in grid connected and islanded mode, would they be same in both conditions? Did you study? Have you considered the step?
Yeah. So, for example, in the islanded mode, if we are trying to control the voltage and the current, the transfer functions or the compensators or the, just give me 1 second. Yeah. So the compensators for the voltage and the current controllers are derived separately based on the linear circuit.
Okay. So my question is did you find any stability margin, like any stability difference, if the modeled inverter is acting as in grid connected mode or if it is working as an islanded mode? Can you comment on that? Can you find any difference on stability? Like, did you find same border plots for both conditions? This is my question.
Okay, if by stability margin you mean transient stability, I haven't done it yet. So all of the work that I've done up until now is for steady state stability, so small perturbations. Uh, I have done the Bode plots. If just 1 second. Yeah, it's on slide 6 if you check. So, I've included one result over there.
Okay.
I'm sorry, do you want me to share the slides?
Fine, thanks.
Yeah, that'd be good. Okay.
No, it's fine. I understood. Okay, fine. Thank you.
Okay, so there's a question in the chat.
In the chat, yes. Is there any load limit for microinverter? Satya.
Right. Okay. So the load have been set around the nominal power that the microinverters had been designed for. So in my case, I had designed the microinverters to extract power from a solar panel that had a maximum power of 300 watts. So the analysis for the loads were done around that range, so 300 to 50. I'm assuming that answers.
Yeah. Okay. Surya, do you want that?
Yeah, so I have one very general question. See, these microinverters have been there in the field for quite some time, right? So I think they're almost at most of the places in place of solar rooftop systems. So what is that value add that your work actually brings in onto the table when compared to the existing ones in the system? Do you have any comment on that? Okay, am I audible, Pawan?
Yeah, you're audible.
Okay, good.
Yes.
Satya, did you understand the question or do you want me to repeat it?
Yeah, I understand.
Okay, go ahead.
So the work that I have shown is the stability of a further circuit that I have designed. So as far as I found, I could not find any stability analysis for
the microinverter circuit that I have done.
Okay, so I think let's not worry about technicalities of it. So let's just say some person who is actually a fellow traveler actually asked you this question. There are already solar rooftop PV systems. Okay, so what exactly is it you did that's actually different? That person has absolutely no clue about stability and transient response. How would you give an answer to him or her?
I would tell him that the system that I have designed can be if he designs it. If he makes it, the product could be used in both grid connected and standalone modes to supply the amount of programmable nominal power.
Okay, thanks. I think there is one follow-up question on the chart.
Just give me one second.
How do we achieve electrical protection when connected to grid if we have microinverters in each panel?
Right. Yeah. So, okay. So there are some passive protection techniques inbuilt in the panel. So if you, the DC-DC stage of the power conversion is has a flyback converter which has a transformer in it. So I'm essentially isolating the panel from the grid. Apart from that, there are some standards that specify how much protection the solar panel should be provided with respect to the grid. So if the nominal voltage of the panel is more than 50 volts, which in my case it isn't, it doesn't have to be grounded. Other than that, there are no specific protection circuits that I had designed for my work. I hope that answers the question.
The microinverter has protectors, has the protector inbuilt in them. That is what is the question.
Okay, so as I had mentioned, I have no active protection circuit designed right now, but passively the transformer isolates the grid, the panel from the grid. So that is actually one of the elements that could be included in the future. Thank you.
Okay, I think we can complete here this presentation. Thank you, Satya. And what would be the harmonics level?
Could you specify the question? Harmonics when?
What would be the level of harmonics? That is what is the question asked by Ajit Kumar.
So if you mean in the transition period, the harmonics where the harmonics peak basically. In the last slide where I presented my results, the clearing time is essentially the time in which the harmonics goes down below the limits after the transition period. So it remains within the IEEE limits for all types of out of sync synchronizations or grid outages. Yeah, so there are no limit to how much okay, so power quality impact on the number of based on the number of inverters in the cluster is also one area that I have yet to look at. Right. So the overall efficiency of the power electronic microinverter that we had designed was about 84%.
I think the next set of questions can be taken offline.
Yeah, actually, we're running out of time. So
thank you.
Maybe Satya, you can answer the questions in the chat itself.
Yes.
Yeah, sure. That'll be fine.
Okay, so with this, we end up the first session. And let us just start with the second one because we really don't have time for the tea break. So yeah, so this session will be based on wind sail and hybrid energy systems. And firstly, let us welcome our industry chairperson, Dr. K. Narayanan from HPCL. Hello, sir. And we also welcome other faculty chairperson, our very own Professor Shirish Kedare.
Hello. Hello.
Hello, sir.
Yeah.
Okay, so let us start with the presentations. First, we have Mohammed Nidhal. So, Govind, can you share the presentation?
So while Govind is sharing the presentation, Arya, where is the tea being served in case if you want to go?
Maybe you can just ask for it right now.
Yeah, go to the kitchen and get the one.
I'm in office, so.
We're definitely missing out on it.
Hello, Narayan ji, Dr. Narayan. Hello. Hello, are you there? Anyway, let's start. Narayan. Yes. Hello, Dr. Narayan. Can you start your video for a minute? Anyway, he is there. Let's begin. Okay, Arya?
Yes, sir. Go ahead, please play the video.
We are not able to hear clearly.
My name is Mohammed Hafiz. I'm second year MTech student from the Department of Energy Science and Engineering, IIT Bombay. And here I am to present the work done as part of my MTP during the first stage. And the title of my project is Techno-Economic Analysis of PV Battery into Integrated Systems. So the objective of my project is to propose a battery storage for an existing PV grid integrated system and then size the battery according to the following two scenarios. One is the PV is independent from the grid and the battery will be providing sufficient backup. And the second one is PV grid are integrated and battery is providing backup such that the grid integration cost, the grid interaction cost is at the minimum. So the third will be to determine and compare the economic viability of PV alone and PV battery system under various scenarios of incentivizing technology cost, electricity cost, and carbon pricing. So this is the topology of the proposed system. So I'm aiming to control the system using the energy management algorithm that I'm proposing and through a set of relays. So as you can see here, when S1 is connected, a load will be drawing power from the PV system, and when S2 is connected, we'll be either drawing power from the battery or supplying power to the battery. And when S3 is connected, we are drawing power from the grid, and when S4 is connected, we are supplying power to the grid. So this is the proposed energy management algorithm. And here we are considering threefold time of use tariff for the electricity price. So the first step will be to estimate the power that is being produced by the PV system, then the load, the state of charge of the battery, and the time of use tariff. So if the power produced by the PV is equal to the demand, then we will be just drawing power only from the PV system. And if the power produced by PV is greater than what is required, then we will be checking the state of charge of our battery. So if the state of charge of our battery is not at the maximum, then we will be supplying power to the battery as well. The remaining power will be supplied to the battery. And if the state of charge of battery is at maximum, then we will be supplying the remaining power produced by the PV system to the grid. And here we have the opposite scenario when the PV power is less than the load. So when the PV power is less than the load, first thing we'll be doing is we'll be checking the battery state of charge. So if the battery state of charge is not at the minimum, then we will check the time of use tariff. And if the time of use tariff is at the minimum at that moment, then we will be drawing power from the grid to supply to the, we will be drawing power from the grid as well as from the battery. And if the time of use tariff is not at the minimum, then we will be drawing power only from the battery. The remaining power required will be drawn only from the battery. as long as the battery state of charge is not at the minimum. And if the battery state of charge is at the minimum, then we will be again checking the time of use tariff. And if the time of use tariff is at the minimum at that time, then we will be drawing power from the grid such that it will make the remaining load as well as it will supply power to the battery. And if the time of use tariff is not at the minimum at that time, then we will be drawing power from the grid such that it will only make the remaining load. So the next step was to model the system, the PV battery integrated system in Simulink. So here I'm explaining different components that was used in my model. So this is the DC-DC boost converter which we will be using to connect the PV system to our load. So the DC-DC boost converter system is working according to the perturb and observe maximum power point tracking system. So as we know in the PV plot of a photovoltaic cell, the perturb and control, the perturb and observe algorithm is like an hill climb algorithm. It will measure power at different voltages at the previous step of voltages, and if the power is less than uh, if the power is less than or greater than what it was in the previous step, then accordingly we will be adjusting the voltage such that we will be drawing maximum power from the PV system. And this is the AC/DC inverter which we are using to connect our system to the grid. And here the triggering signal will be coming from the energy management algorithm that I had proposed. So these are the equations that we had used to size the AC/DC inverter. And next was to model the solar PV cell. So here we are using the single diode model, and so this is the schematic diagram of the model. And then here we are testing out the model that I have developed using the various inputs, and we are plotting the IV curve as well as the PV curve of the solar cell, and it is getting plotted as expected. So our model is working as expected. And this is then the bidirectional DC-DC converter which we are using to connect the battery to our load. So the DC-DC converter is again getting signal, the control signal from the energy management algorithm, and it will be supplying or tracking power from the system according to the output from the energy management algorithm. So this is the layout of the total system, the PV, battery and grid integrated system. So this is the result of the system when we are giving a constant load. So as we can expect, with the increase in irradiation, the power produced by the solar PV is increasing, and also we are supplying power to the battery. Here the negative IB shows that we are supplying power to the battery, and the state of charge of battery is increasing, and during the low irradiance system we are drawing power from the battery. So the remaining work during at the time of my stage 1 project was the techno-economic analysis and scenario generation. So this is my MTP work. Thank you everyone.
Yes. Thank you. Any questions?
We do have Nidal here, so if you have any questions, you can ask.
Okay, so maybe I'll ask a question. What is the criteria for management? Will you do the minimum cost or how will you go?
Yes, sir. The management criteria is to reduce the grid interaction cost.
Any other criteria like availability all or differential tariffs? Anything like that considered?
Yes, sir. So it's a threefold tariff. Based on that, I'm trying to reduce the grid interaction cost.
Okay. Okay. So So at what distance it's possible to integrate its advantages to integrate the PV to grid, and at what remoteness it is not? Can you comment on that? Are you able to get the question?
Yes, sir.
Suppose I'm in a remote village.
Okay.
Okay. Now how remote I am, how much away, how many kilometers away from the grid I am, does it dictate whether I should have battery or I should integrate with the grid?
Sir, I hadn't considered that situation. So,
Okay, but yeah, that's fine. But your comment, because you are in the field, do you think it's always advisable to go for grid integration or not?
no, sir. At times, it's better to have an islanded system where
Okay.
battery is providing the sufficient backup.
So what will be the criteria to decide that?
It will be the, from my point of view, it will be the cost and technological challenges in providing grid supply to that area.
Okay. 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 Any other question? Yeah, there is question in the chat, I think, no? Is perturb and observe method above advantage over other MPPT methods? Okay, Ajit Kumar has asked this question.
So the advantage of why I chose perturb and observe algorithm was it was simple to implement and effective.
What do you mean by effective?
Like we are able to achieve the aim of having that algorithm, that is to supply the maximum power at all the times. At the same time, it is very simple to implement.
Okay. I think we have no more questions, so let's go to the next one, Arya.
Yes, sir. So next we have Manoj Vishwakarma. Manoj, are you here?
Yeah, hi Arya. Can you hear me?
Yeah. Just a second. I'll share my screen. Now, is it visible?
Yeah, it is now. So you will be controlling, right?
I have given you the control if you want.
Okay, I will be controlling then. Thank you. So hello everyone, I am Manoj Vishwakarma. I'm a final year 2 degree student in Department of Energy Science and Engineering. I'm doing my project under Professor Zakir Hussain Radha, and my project topic is techno-economic analysis and ancillary service support from hybrid wind PV powered water treatment plants. Okay, so the project objectives are first, in this project, a techno-economic analysis has been performed for a grid-connected wind PV battery system for application of desalination or wastewater treatment plant. In my case, I have taken reverse osmosis desalination plant as a local load. So within this, the first objective is to first choose the plant specification and location. Then the mathematical and cost modeling of the system components are done. And then the optimal sizing of all the system components of hybrid renewable energy system, which includes PV, wind, battery, and water treatment plants, which is the plant's capacity and the water tank of the desalination plant. The second part of the objective is to do the dynamic modeling of hybrid renewable energy system powering this water treatment plant on Dick Silent Power Factory, which is a power system simulation software. And the last part is to how this plant can provide the ancillary service support to the grid while supplying power to this local load. So our focus will be on inertial frequency support, primary frequency support, and the black start capability, specifically from the battery. So the plant type is a grid connected common DC bus based wind PV battery system, as you can see on the right hand side of the picture, the slide. And here the PV, wind, and battery are connected on a common interface, that is DC bus, and the RO plant is connected in the AC side of the system. So the plant load will be what a reverse osmosis plant. This reverse osmosis has plant has been chosen as these desalination techniques are highly energy intensive, costing us around 50% of the energy, like energy share is the 50% for the water production cost. So I'll be sizing the plant for 400 million liters capacity of RO, and the site has been chosen, namely Chennai, that is where an upcoming plant is going to come. So data has been taken from that site. So before moving to the optimal sizing approach, the PV, wind, and battery are modeled using the standard equations, which have not been mentioned here. And so I'm directly focusing on the optimization method. So to evaluate the economic feasibility of the system and the reliability of the supply, an objective formulation has been done to minimize the net present cost of the system components. And in this, the decision variables were the PV array size, wind turbine size, and what is the battery capacity, and what is the plant rating of the RO system, and what is the water tank level capacity of the RO. So a meta-heuristic optimization procedure has been found more suitable for this objective because it is found that conventional methods are not that efficient or accurate compared to these meta-heuristic optimizations. So I've chosen a very simple and understandable optimization method, that is particles of optimization, where it is based on a popular search-based method, where each particle denotes the solution candidate, and so it is characterized. Each solution candidate is characterized by its velocity and position, which can be understood from these two equations, where velocity V can be divided into three components: inertial component, cognitive component, and social component. So the particle, or you can say solution candidates, changes its position according to its personal best, that is the cognitive component, and according to the global best. So after each iteration, the particle's position is evaluated by putting it into the objective function, and then these position can be changed. And the major reliability constraint in this optimization, as it is grid connected system, that is loss of load probability. It means the amount of time that the grid is not available to supply, so the local renewable energy source is not able to supply the load. So it is kept at a bar of 0.1. So the proposed management strategy is, so in this I have described the 6 modes depending on the availability of renewable energy, that is P renewable, and so P renewable accounts for PV and wind. So depending if the renewable energy is sufficient to supply the desalination plant load, or if it is if the plant is empty to take water from the RO plant. So depending on that, a plant will be operating in 6 modes. So if the energy is sufficient, the desalination will be on, as in mode 1, 2, 3, and 4. And if the plant energy is not sufficient to run the plant, that is mode 5. And if the tank is not have sufficient capacity to take more water, that is mode 6. And depending on the availability of battery charge, battery will be charged and discharged, and the electricity will be sold to grid or bought from the grid. The optimization results, as I told, there were 5 optimizing variables, design variables. The PV capacity have got around 85.4 megawatt. Similarly for wind, battery, desalination plant, and desalination water tank capacity. So on the right hand side, you can see the operating 100 hours of operation of the plant. The dotted line shows the load curve, and the light blue line shows the generation from PV and wind, that is P renewable. So then the load, it is excess power and it is supplying to the grid. That green curve shows it is supplying to the grid. And whenever there is a deficit of power generation, that is blue curve below the dotted line, it shows that there is a deficit and electricity need to be either supplied from battery, discharging a battery, or from supplying to the grid. So the final cost of water production came around to be exactly 50.03 rupees per meter cube. Comparing with the current costs, which ranges from 10 to 50 or 60 rupees per meter cube, depending on the desalination technique used, we have focused only on the RO, as it is only depends on electricity rather than other techniques which are like multi-flash or all that depends on thermal. So the result also shows the variation of composition of cost for different components. So where RO plant percentage is highest compared to the other cost, and this negative cost of the grid shows that there is a surplus of electricity that has been supplied to the grid and revenue has been earned from the grid depending on the tariffs. And on the right hand side, water tank level has been shown, and it shows that there throughout the year water tank level is sufficient to supply the water. And as you can see, it is pretty high, as we have taken care the days of autonomy, that is the plant tank level should be enough to supply water to the city for 2 days if there is no electricity supply. So moving on to the next part of the project, that is ancillary service support from battery energy storage system. So these ancillary service support are the additional services that are required for the operation of grid within acceptable limits for security of power supply. So these usually include frequency support, voltage support, black start capability, contingency, and flexibility reserves. So why are we looking into this? Because due to the higher penetration of renewable energy sources, these cause major problems to the grid. For example, reduction in system inertia, which means that a grid has to maintain a certain inertia for the smooth operation of the grid. And so these renewable energy sources are mostly converter interface system, and these provide little or no inherent inertia to the system. Another problem posed by these renewable energy sources is uncertainty and variability in power supply. Due to this, that is the undispatchable nature of these sources tends problem to the grid security. So our focus is on to supply inertial and primary frequency support, specifically on battery. We can also supply these services from PV and wind, but our focus is on battery, how these battery can provide. Where actually battery will also be supplying energy in the deficit periods, and here we are using it also for the inertial and primary frequency support. So having a nature of battery that is instantaneous power supply, we are using batteries, and these batteries can be sized for this application according to the power imbalance in the grid and what is the maximum rate of change of frequency during any frequency deviation. So currently I'm modeling the system into the power factory Dixisland, and the next phase would be to implement this primary and inertial support for the battery. And I'm working on the system to if the system can, what will be the size for n-1 contingency of the power of this 12 bus grid model, and to study the effect of different battery sizes, if it so to cater the different penetration of renewable energy sources. Yeah, thank you.
Thanks, Manoj. Any questions from audience?
Manoj, this is Kuldeep. For this optimization, which software you have used other than Dixisland?
Yeah, I have modeled the system on the MATLAB. So whole optimization has been done on MATLAB.
Thank you.
Yeah. So for the battery, I've taken a single decision variable, that is the like a unit of the battery consists of 1 megawatt and 4 megawatt hours. So this is the unit rating of a battery, and so this has been catered into a single decision variable, that is the battery capacity. So finally, the battery capacity. Yeah, let me show you.
So you're answering that question, what is the sizing of battery bank, right?
Yeah.
Can you tell me the number of slide? It was lagging, so I stopped your control.
Okay, you can go to slide number 4 or 5. So it is 57 megawatts and 220 megawatt hours.
Which one exactly?
Yeah, okay, yeah. You are on right slide, slide number 6. The battery capacity is 57 megawatts and 228 megawatt hours. And looking at the cost of water production, the optimization shows a feasible approach to this, like tackling this energy intensive cost for water desalination.
This is the real problem you have tackled, or just on a working plant you have taken the data?
So, sir, I have chosen the location for the upcoming plant. So there were assumptions like, the plant will be supplying continuously constant amount of water, that is 400 million liters per day. So that is the biggest assumption, and actually that is more realistic in a way, because these plants have been told by the water supply management that you have to continuously supply water irrespective of the situation.
That is really great to get help from students for setting up a plant. Great.
Yeah.
Thank you, Raghuramji. So any other question? Kumaresh, yeah, you want to ask
hello?
or I should ask? Kumaresh, you can go ahead.
Yes, Kumaresh.
Yeah, thank you. Okay. Hi, Manoj. So I have a general question.
Okay. We have a question from Kumaresh. So let me answer that. So Kumaresh,
please read the question also so everybody knows it.
Yeah, if the 2 days of autonomy condition is eliminated, what would be the possible cost reduction? So because of these 2 days autonomy of the plant, so it means that water tank should have enough capacity to supply water to the city for 2 days. So this has been a design condition put by the water, like the plant designing authority. That's if we feel eliminate it, definitely the cost of the tank will be removed from that. So that we can do the calculations.
Okay, cool. Thank you.
Hi, Manoj. I have a general question. You may answer in the time of like a yes or no form. So my question is, generally the peak demand occurs in the time like a 7 p.m. or 6 p.m. or 8 p.m. in Indian scenario. So
Yes.
one of the conditions you said that the proposed optimization method is able to feed the power to the grid as well. So
Yes.
is your proposed method able to feed the power at the peak demand scenario at the time of 7 p.m.?
Yes, actually, because you're talking about these like the residential loads, those have a variable curve, like we have 2 peaks, but in this my local load is desalination plant, which is kind of fixed load. You can see in the dotted curve. So during the peak operating hours, like in the daytime, the excess power has been supplied to the grid, which can be shown in the green curve, the peak. Yeah.
Oh, okay. Yeah. Thank you.
Any more questions? Okay, I have a question, Manoj.
Yes, sir.
How do you manage the wastewater brine coming out of RO?
Okay, so sir, since my focus was not more towards the water management, so usually from the process of usual what is followed is if there is 100% water coming, only 40% of water is recovered in the pure form. The rest of the 55% is again sent back to the sea. So which is a major problem posed by these desalination methods. That's why these desalination methods are usually not preferred techniques for a country like India.
Yeah, so your optimization doesn't include the management of that.
Yes, sir.
Okay.
Okay, so let's continue with the next presentation. Also, before that, I'd like to remind the judges to evaluate the presentation. If Narayan sir could hear us, sir, please keep evaluating. The questions could be answered in the chat itself by Manoj. So let's go ahead. So next we have Lomesh. So yeah.
Hello everyone. My name is Lomesh Tigaria, and in this talk I am going to present on the flow restart behavior of a multi-plug pipeline filled with a waxy crude gel. Waxy crude oil production in a low ambient condition is significantly affected by the presence of precipitating components. The transportation shutdown in this low ambient condition leads to a complete gel plug pipeline, which requires a high pressure to clear the gel pipeline. The increase in pressure requirement depends on the gel strength, which itself depends on the shear and thermal history imposed during the gelation process. The increase in pressure requirement is always limited by the pipelining material as well as the pumping capacity. Therefore, in the present work, we have considered the pressure propagation process and flow restart behavior of in a gas separated gel plug pipeline, which is also called as multi-plug pipeline. The presence of gas pocket in between the gel segments increases the overall compressibility of the gel pipeline system, leads to ease in the flow restart process. To investigate the pressure propagation and flow restart process in a multi-plug pipeline, we have numerically simulated the mass and momentum balance equation together with volume of fluid method to deal with the multi-phase system. In addition, the updated value of the velocity field is used to calculate the deformation in the gel material. In addition, the total resistance offered by the gel material is the sum of the viscous and elastic resistance. To understand the pressure propagation and flow restart process in a multi-plug pipeline, here we have compared our multi-plug result with the single plug gel pipeline system. In the case of single plug pipeline system, the applied pressure quickly diffuses in downstream direction, which leads to a low deformation in the gel material, which is unable to overcome the elastic resistance. Therefore, in this case, there, the flow restart is unsuccessful. However, in the multi-plug pipeline, the applied pressure quickly diffusion of the applied pressure is controlled by the high compressibility of the gas pocket, which leads to a high pressure gradient is developed across the first gel segment, which causes a high deformation of the first gel segment, which is able to overcome the elastic resistance of the gel material. The movement of the first gel plug into the gas pocket compresses the gas pocket. Compression of gas pocket leads to a progressively a higher pressure gradient is developed across the second gel segment, which leads to a development of high deformation in the second gel plug. The combined effect leads to a successful flow restart in the multi-plug pipeline. To further improve our understanding, we have also considered the time evolution of elastic forces in the multi-plug pipeline. It can be seen that the elastic resistance of the two segments decreases in two stages, demonstrate the sequential breakage of the multi-plug pipeline system. In addition, we have also drawn the constant movement of the gas pocket in the multi-plug pipeline system, as shown in the figure 5. To demonstrate the effect of the gas pocket, we have also considered the flow restart process in a longer pipeline. Here we have considered a 3 gas pockets separating the 4 gel plugs. In this case also, the stepwise utilization of the pressure force leads to a sequential development of high pressure gradient in the each gel segment, which leads to a successful flow restart in a longer pipeline. Here it is important to note that in this case the pressure applied is equivalent to the Bingham number 1, which defines the ratio of the total shear resistance offered at the pipe wall to the pressure force applied at the inlet. Further improve our understanding, we have also considered the flow restart process in a small gas pocket separated gel plug pipeline. In this case, a small displacement of the first gel plug is sufficient to compress the gas pocket, which causes a pressure quickly developed across the second gel plug. However, in this case, the total deformation is unable to overcome the elastic resistance. This leads to an unsuccessful flow restart in this case. Therefore, it can be concluded that gas pocket delays the pressure propagation in downstream portion of the pipeline. This delay is directly proportional to the gas pocket compression time. A large pressure gradient across the first gel plug results in early degradation. This reduction in gel strength of the first gel plug present a favorable condition to establish a high pressure gradient across the second gel plug. Therefore, we can conclude that the small time scale of compressive diffusion is further enhanced by the large time scale of the gel degradation. These are the references considered in the preparation of this presentation. Thank you for your kind attention.
So we can have a short Q&A session of about 4 minutes. So let's continue. So we have Lomesh here. So if anyone has any question, you can ask him.
So let me ask something which I know about ONGC and other things. So what are the areas where this low, like this 4-point problem is occurred? Which kind of oil, which basins, where? Any idea?
4 point,
The
4 point of
waxy, where are the waxy crudes in
yes,
India?
sir. Usually the 4 point of the crude oil lies in between the 22 degrees centigrade to the 26 degrees centigrade in the India. And if the temperature falls below this temperature, as the subsea temperature is much smaller than the this temperature is around 4 degrees centigrade. So any shutdown in this condition leads to a formation of a strong gel-like network, which is
So this is more relevant for the offshore problems.
yes, sir. It is related to offshore problem or some low ambient conditions, low ambient atmosphere weather.
Okay. So what is typically done otherwise? I think pipelines are heated, right?
Pipelines are heated, but that is not the economical way to restart the flow, as the pipelines are very long. As usually, it is vary from the 100 meters to 300 kilometers. So the heating complete pipeline is not economical. So usually the high pressure is applied to remove the gel structure or break down the gel structure. So, so we have analyzed the. That's why we have analyzed the pressure propagation in a longer pipeline, and we found that the if a gas pocket is there in between the gel segments, the formation of the gel increases, which can easily restart the flow in a longer pipeline.
Okay, but this is more relevant for offshore because where heating is impossible.
Yes.
And gas also comes in. Gas, of course, is separated initially, isn't it? Yes. But there can be a pocket. Yeah.
Yes.
So, Dr. Narayanan, do you have any question? Because HPCL also have a lot of pipe. Don't know anybody from ONGC who has the offshore pipelines?
So actually, this problem we are experiencing in where there are waxy crudes, and you require pumps which should have a huge shut-in pressures. So it's a good idea. I think what he's suggesting is that instead of high pressure pumps, we can utilize the compressibility of the gas to move it. Am I right? That is the core.
Yes,
idea which I got. Yeah. Because we have not experienced such kind of problems in offshore. Though yes, because offshore we've been moving and offshore crude is not that waxy. We have problems in wherever these are waxy crudes, high viscous crudes in onshore fields in Mehsana, Ahmedabad, such kind of places we are facing.
So it's also onshore problem, not only offshore.
Yes, sir. Yes, sir. That's right.
Yeah. Thank you, Bhatiaji. Bhatiaji is from ONGC Academy, by the way. Thank you. Anybody else?
Yeah, I'm from Offshore Engineering Services. The point is well taken here. Like you have proposed that the compressibility of gas can be utilized for initiation of the flow.
Yes,
but many times when we run the flow assurance and the fluid is of such nature that we don't get that kind of a presence of gas. And in that case, there is absolutely no other option but to heat the pipeline. And that's how in Eastern offshore, there are certain pipelines which are heated also. I mean, the point is good, but just what I'm saying is many times we're not left with that option.
Okay. So we have we can introduce the gas uncompressed gas in between the in between the gel segments, so that we can further increase the compressibility of the, and we can also break the a long gel into a smaller gel segments. That is the one of the possible way to increase the overall compressibility.
Okay, you have got a direct feedback from the operators, ONGC offshore.
Yes, sir.
Right.
Thank you.
Okay. Thank you, Team ONGC. Glad to hear you again after quite some time. Yeah, thank you, Lomesh. I think we can stop here, Arya, for Lomesh.
Yes, sir.
Go to next one.
Yes, sir. So next we have Alok Kumar. Alok, if you're here, then we can start the video. Govind, please share the screen.
Good afternoon, everyone. My name is Alok Kumar, and I am a PhD student working under Professor Sumit Singh. The title of my current work is Thermal Management of Electrical Devices using Heat Pipe Technology. So, as we know, all electrical devices which we use in day-to-day life dissipates heat. And in the world where we are approaching towards miniaturization, we are guided to innovate a very passive heat devices systems. So in order to that, there are many heat management systems technologies, but one of them which is very promising is called heat pipe technology. So what is heat pipe? Heat pipe is generally a two-phase heat transfer device which is capable of transferring large quantities of heat with minimal temperature drop. So every electrical device has a heat source, so that works as a heat evaporator in a heat pipe. On the other hand, we have a part of the device where we dissipate the heat, so that is called condenser of the heat pipe, and the area in between that is called adiabatic section. So one such type of heat pipe is called pulsating heat pipe, which the name pulsation is due to its pulsating nature, and it can be of two types. One is closed loop and the other is open loop. So a pulsating heat pipe has shown its capability of operation into varying gravity as well as at different orientations. So these properties makes PHP very promising candidate to use in space applications. So in my further slides, I will mostly focus on PHP application in the space. So the main problem with using PHP in space applications is that still we don't have the usual characteristic or operating characteristic of the PHP. That is due to the involvement of many processes. So the instabilities in PHP occur due to fluctuation and due to non-uniform heating and cooling of the electrical device, and also due to unsymmetrical liquid vapor distribution. So after some time, we see self-sustained thermally driven oscillating flow, which is very hard to model. So for that, one approach could be that if we can model a heat pipe mathematically, and then we will see what is the nonlinear behavior of the system. Since the heat pipe is involving many processes like interfacial mass transfer, capillary force, Boltzmann stress due to viscous action, phase change, surface tension, gravity. So what we did, we took small control volume, which is consisting of two vapor bubbles sandwiched between the liquid sludge. So all these processes were mathematically modeled, and we wrote momentum and force balance equation, and then we simulated it, and we got some results. So this is the temperature profile of liquid slug and vapor plug. So for a given temperature of the ball of the pipe. So we can see from in the zoomed part that the linear profile, which is without the pulsations, is actually for the vapor, and the oscillatory behavior is for the liquid slug. So that shows after certain time, the vapor is going to settle, but the liquid plug will, the temperature of the plug will fluctuate. That makes, on the other hand, that makes the liquid slug oscillate throughout the operating time. So here in the zoom part, we can clearly see that the liquid slug is oscillating. So from these two results, we can at least conclude that if we are able to solve the nonlinear behavior, that is, we are not truncating the higher order terms in the mathematical models, and we are taking them into also consideration, we can find out the predictable chaotic behavior or any other sort of instability in the system. It then can be understood using mathematical modeling that would make the pulsating heat pipe applicable for the space applications. So that is the basic motto of current work. Thank you.
Thanks, look, Alok. Any questions? Okay, so how compact this can be, by the way?
Alok, you're muted.
Hello. Yes, sir. Depending on the nature of the need, like it is currently it has been used in the computer systems also, the PSP. So we have called a new idea is called miniature heat pipes. So depends on the need, it can be compact.
So how what do you mean by miniature? It's in millimeters or centimeters or micrometers?
So the current system which I was modeling was the diameter was in mm only. 25 was the diameter, and the length was in centimeter.
Length was in centimeters.
Yes.
Okay. Okay. Gotcha. And it has to be how it can't be tilted, right? At a appropriate.
Yeah, PHP, because its LYD ratio is very low, so it has the current literature shows that it can be tilted. It is operating in different tilt angles also. So that way, yes. So that way, it is very like people have seen the potential to use in the space applications.
Okay. Okay. So normally gravity is necessary for heat pipes, but here it's not.
Yeah, sir. The gravitational component will not dominate in case of pulsation.
Yes.
In conventional heat pipes like thermosiphon or any other one, where we have large like a scale of the dimension, there the gravitational components actually is the dominant one.
Yeah.
Yes.
Any questions from any audience? You can put it in chat also if you want. If not, we can go ahead, Arya.
Okay, thank you.
Thank you.
Sir. Everyone, yeah.
Yes, yes.
So the next presentation we have is of Aditi Mahajan. So we can play her video.
Hello, good afternoon everyone. My name is Aditi Mahajan and I'm currently pursuing my 5th year of energy engineering here at IIT Bombay. And I'll be presenting my dual degree project, which is based on multi-criteria decision analysis for energy systems. I've been working under the guidance of Professor Shirish Kedare. So throughout the course of this presentation, I'll be covering the why, what, and how aspects of my project, and then I'll be explaining the practical case study that I'm working on. So firstly, coming to the need for this research, we know that India is one of the fastest developing countries across the globe. Our GDP is estimated to be around 35 trillion US dollars by 2050. So to sustain this growth, naturally the energy, fuel, and electricity demand of our country is going to increase. In fact, it is estimated to increase around 2 to 3-fold times by 2030. So it is high time for us to explore the real options to accommodate our future needs, like electric vehicles, renewable energy, biofuels, etc. So that brings me to an important question: what to invest in, how to invest in it, and where to invest in, and how to back it up with a logical reasoning. So all of these questions I have been trying to answer through my project. So coming to the what aspect. So firstly, I'll talk about hybrid power systems. They consist of two or more energy conversion systems or two or more fuels for the same device, which when integrated overcome limitations of each other. Hybrid systems, especially in case of renewable energy, can address limitations in terms of fuel flexibility, efficiency, reliability, emissions, and economics, of course. So my goal is to come up with the best possible, to figure out what is the best possible hybrid energy scenario for any given location using multi-criteria decision analysis. So for this purpose, I have chosen a case study based on my village, which is Popnar Kala. It is based in Madhya Pradesh. So in the figure one, you can see the schematic of Homer, the software Homer components. So as you can see, the system has PV, wind component, biomass component, the conventional grid, battery backup. So this is from this figure, you can see that a hybrid system can have different kinds of combinations. Like it can have PV plus wind, or it can simply have wind plus grid, right? So my goal is to understand which one will be the best for my village. So the methodology for this project is in the step one, I define the goal. So for this project, I'm focusing on the electricity demand, electricity needs of the households of the village. So after this, I did a quick demand assessment for the village, and I also contacted the nearby substation. They helped me with data. After that, I researched for technical and economical component inputs that I can feed for the Homer components. Once this was done, all the components were modeled in Homer software, and I generated feasible hybrid renewable energy scenarios. Now the next step is to compare these scenarios using multiple criteria. We know that it has become more and more difficult to see the world around us in a unidimensional way today, and to use only a single criteria to compare different alternatives, especially in the space of energy, does not seem fair given the position that India currently is in. Right? Most of the time, the cost is the most important factor, but we also need to look at the social, the environmental, and of course, technical aspects. So this is a quick summary of demand assessment. The different different types of loads that are present in different types of houses in my village. This is a load curve, which I got from the substation. The peak load is around 1,577 kilowatt. This is a quick summary of wind and solar resource assessment. Now coming to the method that will be used to compare these alternatives. Multi-criteria decision analysis essentially uses both qualitative and quantitative data to compare different alternatives using different criteria. One of the methods, TOPSIS, which falls under the bucket of MCDA, stands for Technique for Order Preference by Similarity to Ideal Solution. It was developed by Young and Wang in 1981. So as you can see in the figure 4, you can see the visual representation of TOPSIS. So different alternatives are there. Using those alternatives, a positive ideal solution, which consists of all the best possible values that these alternatives have for different criteria. And then there's a negative ideal solution, which is the worst possible solution. Now, in TOPSIS, we calculate the distance of all the alternatives from both of these ideal solutions, and the hybrid system that is closest to the positive ideal solution and that is farthest from the negative ideal solution is supposed to be the best solution. So here I have tried to summarize the different criteria that I'm going to use to compare my hybrid systems. So as you can see here are the economic ones, like initial investment cost, operational cost, cost of electricity, payback period, etc. Then there's this is the social bucket where I am looking at the employment generated, the social acceptability, the land usage, and then there's the technical one, unmet load, capacity factor, etc. And then lastly, environmental one, like the car CO2 emissions, the noise and visual impact, etc. Right? Now, using all of these criteria, the final goal is to identify the best hybrid system for the village using TOPSIS. Thank you so much for your time. These are some of the references.
Thank you, Aditi. Any questions? Should I ask the questions? We are going to apply it to your village.
Yes, sir.
Yeah. So what about the social costs or
Sorry?
employment generation, other cost? Those criteria are taken. Suppose
Yes, sir.
providing this energy will benefit in employment generation.
Yeah, yes. So
How
I'm
that
looking
can
at the
be? So it can be taken care into the software.
no, the software only gives me the feasible hybrid solutions. And to compare these solutions, I can include a social criteria, as you said, the employment criteria. So I'm actually looking at the direct employment that is generated because of hybrid systems in the village. So that would be inputted, that I'll input in the MCDA method.
Yeah, so there exists a method which can take also that into account and select which is the best one.
Yes, sir.
Depending on the weightage or whatever you create.
Yes.
For that criteria.
Yeah.
Yeah. But other social benefit quantification may be a problem, right? How do you do that?
It will depend on what criteria. I mean, it will vary from criteria to criteria. So I think the primary thing that I'll be doing is referring to the current research that already exists. And secondly, I'll be talking to people. It is easier for me to connect to the people in my village. So I think that will help me look at social aspects from a better angle.
Yeah, there is a question here from Ajit Kumar. Which model is finally selected, deployed?
Okay, so currently I haven't chosen a final model because it will be done after I apply MCDA method. After modeling my system components in Homer, I got different feasible solutions. For example, in the system of PV plus wind, I have the capacity for PV and the right capacity for wind. So I have the solutions in my hand. Now I have to compare them using the MCDA method, so that I'll get the final answer towards the end of my project.
Another question out over there. Amol Srivastav.
Can similar model be used for industrial hybridization? Yes, it can be. Actually,
Industrial hybridization based on process load condition.
Okay, based on process load condition. Okay, so basically, instead of a village, you are talking about an industry with a different load, right?
Yes, yes.
Okay. So yeah, it can be. Actually, in 2018, Government of India, they also introduced the National Renewable Energy Hybrid System Policy. So they plan on coming up with the optimal numbers for land uses and for integrating transmission lines and the hybrid renewable energy systems across India. So for that, they'll be doing this. So I think it can be applied to the industrial load systems also.
Yeah, so suppose it's a process electrical load or process heat load. That can also be done?
Heat load, I think yes, it can be done, but I am currently focusing on the electrical load.
Okay. Ajit ji, you have anything to say? Ajit Kumar? Any other question? What softwares or algorithms are used?
Yes, so only one software is used. It is called Homer. It is by NREL. And for comparing the solutions, I am using TOPSIS, which is a multi-criteria decision analysis method. So only these two.
Okay, I think we can go ahead. Arya, thank you, Aditi.
Thank you, sir. Thank you, everyone.
I think someone had raised his hand.
Yeah, please go ahead.
Yeah, actually, Arya, it was me. So like I just had a small question. Like there might be a lot of studies that might have happened, right, already in the research that are comparing different technologies like solar, wind, etc., that you have considered here in Homer, right? So what is it that you are doing different, and could you not just import those studies into your village and then just give the results? And that would also be I think a great
Yeah.
initiative. But what is it that you are doing different over here?
Yes, so I'm not comparing different technologies per se. I'm comparing the actual solutions that can actually supply for the demand. So for example, PV can be the most sustainable solution for my village, but it cannot meet the demand, the load demand. I have to have wind plus PV plus biomass, some hybrid system, or at least a battery backup. So that's why I can't just compare, technologies to get the right answer. I need to look at the practical energy scenarios. So that is something new that my project brings on the table. Does that answer your question, Govind?
Yep. Great, thanks.
Okay, so thank you, Aditi. Now we go forward with our last presentation. We have Vaibhav Gavra. Are you here?
Good evening, everyone. I am Vaibhav Gurav, and today I am going to present my master's project on the topic hybrid solar PV, wind, and battery power plant, its control and operation, power hardware in loop study. Motivation of the project is due to increased electricity demand and climatic issues created by conventional power plant. There is paradigm shift from conventional energy sources to renewable energy resources, where hybrid power plant provides the effective solution due to complementary nature of solar PV and wind energy resources, high energy output, and high plant load factor. The main objective of the project is to model, design, control, and operation of hybrid solar PV, wind, and battery power plants to exploit its main grid support functions such as voltage support, inertial, frequency, and reactive power support, and then validation of the results via MATLAB simulations and then real-time simulations. This graph shows the annual new installation in world in terms of gigawatt. From this graph, we see that till year 2015, wind installed capacity is higher than the solar PV capacity, and after 2015, the solar PV capacity increased enormously than the wind installed capacity. Now coming towards the methodology of the project, first one is MATLAB modeling of hybrid power plant, which is identical to the hybrid hardware setup which is available in the lab, having the capacity of solar PV of 1 kilowatt, wind power plant of 1 kilowatt, and battery having the 96 volt and 26 ampere hour of capacity. In case of PV plant, unidirectional DC-DC converter, that is boost converter, is used to track the maximum power point by using P&O MPPT algorithm. In case of wind power plant, machine side converter control is used to track the maximum power from wind power plant. In case of battery energy storage system, bidirectional DC-DC converter, that is buck boost converter control, is used with the help of current reference and injecting power to the grid whenever required. To obtain the voltage support, reactive power priority based voltage support is provided to MATLAB hybrid power plant model. To obtain the fast frequency support, inertial and primary frequency control is implemented in hybrid power plant model in MATLAB. And last is the grid support services from hybrid hardware lab setup. Now coming towards the results, first we will look at the hybrid power plant parameters. From the wind power plant, that is at the end, after the machine side converter, we get the DC power, it is 1 kilowatt from the wind side. This one is the solar PV power, whose value is approximately whose average value is 950 watt. From battery's discharge current rating is 5.2 ampere. So battery discharge at 5 ampere for 9 seconds. So we got the battery power, that is 480 watt. Here is the power injected into the grid. As we can see, 1000 from PV, 1000 from wind, and 480 from battery. So 2.48 kilowatt power is injected into the grid. At the time of 5 seconds, voltage dip of 0.8 per unit, that is the system voltage of 0.2 volt, is given to the system. So we can see the power injection is reduced, but the power coming from the sources is same. That is why we see here there is increment in the DC link voltage during that operation. So we use the crowbar protection. Whenever DC link voltage is increased beyond its limit, then the extra power which is coming in the DC link, which is dissipated through the resistance, through the crowbar protection. Here we can see the active and reactive power injection depending upon the grid requirements. And here we see the small increment in the reactive power at the time of voltage decrement. Now voltage support from hybrid power plant hardware. Voltage support from the hybrid power plant hardware setup. Here we see the PV and wind hardware setup results. Here we can see the at this time the fault is created. That means the 0.7 per unit voltage is dipped to 0.7 per unit. At that time, reactive power injection is increased into the grid. This graph shows the ID reference, IG actual, IQ reference, and IQ actual values from the hardware setup. This diagram shows the representation of LVRT grid code regulation, Indian LVRT grid code regulation, the model which is designed, which is able to follow the Indian grid code regulation. The black line represents the Indian grid code LVRT regulation, and the blue line represents the model which is followed the grid code regulation and able to recover the fault within the certain time instant. Now to conclude the topic, hybrid power plant, which can be the potential reliable source of power due to intermittency of both sources of wind and solar. Next is modeling, design, control, and operation of laboratory setup of hybrid power system is understood. Then reactive power priority based voltage support is obtained from hybrid solar PV and battery power plants. Now future work of the project is to implementation of the control strategy to obtain the frequency and voltage support from MATLAB hybrid power plant model. Then real-time hardware simulation to study inertial and frequency reserve support. Thank you.
Any questions? Students, any question? So what's a different thing that you have done, Vaibhav?
Yes, sir. So, sir, intermittency of solar PV and wind, as we know. So we are combining the both sources like solar PV and wind, but at the same time, as we can see the intermittency of sources, we are providing the battery support. Along with that, grid support solutions we are providing whenever there is a fault or disturbance in the grid side.
Yeah, but that is done, right? Meaning there are also ground-based systems like in Pune, Reserve Bank of India Training Center has such a wind PV hybrid system for last 10 years. So what's a new thing that you are doing in it? Or is there a different approach for doing it or what?
Yes, sir. Battery system is also integrated along with the wind and PV integration. So that can be the reliable solution along.
Yeah, that's right. But is the method new or what? How does it compare with the conventional method, your method? How does it compare with the conventional method?
Sir, the implementation of grid support services like voltage support and frequency support, as we know, along with the integration of the hybrid power plant, we have to make sure that as the renewable power integration into the system is increasing day by day. So our new power system should behave same like the previous, that means the conventional power system. So it should be able to support the grid support services that I am able to demonstrate through this control system. Like whenever there is a fault, then during that during that fault or disturbance time, hybrid system would be able to support the reactive power and at the same time frequency support if there is any frequency disturbance in the grid. That means the active power imbalance in the grid.
Okay. Okay. Anybody else? How reactive power is supported? Ramesh is asking this, Mr. Ramesh.
Yes. So for reactive power support, reactive power based voltage support can be implemented. Implemented in grid side converter. That means the inverter side, so that reactive power is injected into grid and the rest of the margin of the inverter is going to the active power command, and both powers are injected. And obviously by injecting reactive power, voltage support is we can get.
So how do you inject? That's the point. How reactive power is supported? How you inject to balance the reactive?
Sir, one control loop is implemented according to the IQ reference versus voltage of grid. That is the curve which is standard curve which we are available for voltage less than 0.5 per unit in the grid side. That time IQ reference command is set at its high value. Reference value at 1 per unit, and rest of the margin of the inverter is going to the ID reference command. So whenever our IQ reference command is increased to 1 per unit, that time the reactive power is injected into the grid. That is the control given to the inverter.
But which gives that power?
Inverter, sir.
Inverter gives the reactive power?
No, sir. Inverter side control.
So where does this reactive power come from? Yeah, how you control is how you answered, right? Fine.
Yes, sir. Yes, sir.
But where does it come from? What's the source of this reactive balancing power for reactive power? Okay, let's get Ramesh. You have any more question on that? Okay, fine. He has no question, so it's okay. Yeah, fine. Narayananji, are you there? Can you unmute and just talk about your comments? Hello. Okay, so I think we are done, Arya.
Yes, sir. So one last thing that I'd like to ask all the people who are here to maybe comment on the event or say a few words of wisdom to our students and also the research students.
Maybe you can also put it in chat, right? Sir, can you score for, yeah. Can you put it in the chat if there are any comments? Is there any format, Arya, for that?
No, sir. A general discussion.
Okay, okay. So how did you like the whole thing, the idea? Any comments from anybody? Anybody from industry?
Sir, namaskar. I am Kuldeep Jain, sir.
Yes, I know.
Namaskar,
Tell
sir.
us anything
Sir,
about
I am finding it really interesting to interact with IIT sitting at my home, and this format may continue even after COVID is over.
Certainly, certainly.
That will help a lot of us to get connected.
I second his opinion. I think this is a very good way of getting more people to listen to the students. I second, Kuldeep, what you're saying.
Thank you, Anuradha. Thank you. I'm sure you're all fine.
Sir, I would like to
I'm
come
Narayan.
in if I'm
Yes,
allowed.
Narayanan.
Yes, sir. Couple of
Yes.
points. I think, being a petroleum company, I'm able to see, we are working on battery technologies, fuel cell and other things. But then finally the product, see, you can make cells, you can make the pack system and other things. But then on top of it, the electronics and the software, which needs to be tuned up. I think when one such proposal also from your side on a PhD candidate would also be required, because we got certain proposals on supercapacitors, on the nano composite materials, and some pitch combustion and other things. But there is something which with the bridge, when you work on all these conversion devices, it's basically electrical engineering also comes into play at a higher level. So I think some such element also some PhD students can also, if they are interested, that you can send those proposals to us as well. Maybe it's not there in our list, which we gave some year back. So that's one thing which I was thinking, because it's finally integration, working on the BMS or for example, fuel cell management system and other things. And those things are, are also equally important. Only then, it would move from the energy, or the electrons would move from the product to the, in an efficient manner, to the system as such, electrical system.
Yes, yes. Thank you, Narayan. Mr. Narayan is from HPCL and he looks after R&D, and we have been interacting. Of course, you can also write to us about such topics, Narayanji. Right, but that's a very good input for you students. So, being from industry, he is, his concerns now. Yeah, and Anuradha, yes, you can also have your comments from industry.
Yeah, I mean, I thought it was a great day. I mean, I have. In fact, I was following the whole day today, whole afternoon. I was very impressed by the quality and the quantity. I must say that, and the presentation types. However, I do feel, and I was chatting also on the side with Surya, that it could be a continuous journey that would probably help, rather than us looking at. I'm now looking at from the industry side. So instead of talking to the students at this point, to enable a good project, enable a project which can be applied or taken to the next level, if we can have this sort of an interaction individually, not an energy day. I know it's a lot of logistics and a lot of issues in that, but if you're really catering to some industry problem, for example, the one who was talking about the transportation, optimization of transition for electrification. I think if an industry input is taken at the right time, it'll be helpful for the industry to follow and then absorb it. Ultimately, I think that's the objective, right? If you're doing an application type of a project, then it's a good idea if that group absorbs it. So a regular interaction with the industry, at least appropriate industry, should be helpful, is what I feel. Because the quality is so good. I mean, it's time we start doing that now.
Thank you. Thank you, Anuradha. So,
okay, just a concluding line that we would like to thank you all for taking your time from your busy schedule and joining us on the Energy Day 2021. Hope that you had a fruitful experience. So maybe you all can join the general channel now.
yes. So we just leave this room and go to the main room, right?
Yes, sir.
Yes.
Sir, can you just fill the scores?
I have.
Okay, sir. Thank you.
So will we be taken automatically to the main room, or we have to log in again?
You have to just leave this room, Anuradha.
Yeah.
There is a leave room button, blue button on the right side.
Okay. Okay, fine.
You just leave, you go to main room. Okay. So thanks everybody from industry, HPCL, ONGC, Cummins, railways, and other industries which I am not particularly aware, but yeah, there are many. I don't know the names and other things, but thanks to all industries taking an afternoon out for us. Let's go to the main room now.
Yes, sir.
Yes. Thank you.
Thank you, everybody.
I could actually not thank Surya sir and Pawan sir personally, so it's
yeah, it's okay. Doesn't matter.
I think a few channels have discussions going on right now.
Yeah.
Yeah,
So
it's done. It's done.
Yeah.
Thank you,
So
sir.
we'll leave this room. Thank you. Thanks, Arya.
Thank you, sir.
Room breakout will be closed in 4 seconds.
Yes.
So we can move this.
Yes, yes, we can.
Not bad. We have 120 people at the end of 4 hours of online. It's very difficult to have this kind of people can't keep staring at the screen for so long.
Yeah.
It's
Yeah.
always tricky.
I think some rooms, I think they have closed the rooms, right?
Yeah.
Everybody's back or what?
All rooms are no, still going on.
Yeah, still
One
going
is,
on.
I think,
I
still
can see
going on.
that. Yeah, 32 in channel 1, 28 in channel 2,
No,
23 in
that
that's
was
old one.
that's old.
Yeah, yeah.
Everything is done. No rooms
I think
are-
now all are done, no?
Yeah.
Sir, every room is closed now.
Okay,
Yes,
so
sir.
we-
So we are done with all the parallel sessions. So thank you all of you for attending the event. I really appreciate your participation and your presence throughout the event. I hope you enjoyed it. And now we will have a small interactive session with our department alumni. We have Mr. Ayush Mahajan and Ms. Nilima Pagana here with us today. Ayush is one of our dual degree students who graduated in 2015 and since then has been a part of tech startups that cater to the energy sector. In 2017, he co-founded PV Diagnostics with 4 other colleagues and is currently the business development head of the company. I call him now to share his experience with the department and also give our students a brief insight into an entrepreneur in the energy sector. Over to you, Ayush.
Hi. Good evening, everyone. Lot of interesting sessions, though I was not part of all the sessions, but I was able to attend a few. Thanks a lot again for inviting me. Happy to be part of the department, at any day and for any kind of activities. So just I think for probably I was speaking with Chaitanya and he had told me, we were speaking about what all things I can share. So I think one of the things that I would speak about with probably with with the students who are already there, that I think the best thing of our department is that there are limited number of students, so you can get a very good opportunity to work along with professors, and the closeness is much more than what you would see otherwise. So that is a really great thing that we used to have. So for us, I mean, at that point of time, for I mean, any other department and all, for us it was very different. So which really helped us a lot in in a lot of work. Our for example, I mean, our core, in fact, our department's coursework is also a lot more proactive, I would say, which helped us in, so there were a lot of project based courses as well. So which kind of helped us in thinking and planning a few things. And I think those project works kind of, for me, led me to nurtured my interest further in the energy sector, because doing while doing those projects and all, my interest kept increasing. So to tell you, in my in our startup, me and Pranav, both of us are batchmates from the department, from the 2015 batch. So out of 4 co-founders, 2 of us are from the department only. And for both of us it worked that way only. That I mean, we wanted to do technical stuff, and when we get into, when we get into IIT, we all of us want to do, but gradually the interests shift. But for us, we wanted to be in the sector, and I think the coursework was such that it kind of helped us. So what I would urge, the students, that keep getting involved in those projects, because those are very, and especially in the energy sector, which is a very growing sector right now, it's very interesting to get into those kind of projects. uh, Also, I mean, speaking from the energy sector perspective, I would say that for us, I mean, because there was an inclination towards getting into the renewable energy sector for me, I kind of, try to find those opportunities where I can get into it. And then, finally PV diagnostics happened for us. So, but what I would say is, overall, if students are wanting to know what is happening, like, there is, of course, I mean, there are so many, I mean, there is everyone, like, there are all the professors, but from a, from my personal perspective, I can share that the solar sector, I mean, the overall, the renewable energy sector is growing a lot, be it solar, be it energy storage, smart grids. At core technical level, at system level, there is so much happening that, I mean, all of you, whatever, work you're doing can have a certain impact. So definitely, I mean, do have your interest, and try to like, I think, in one of the sessions, I think Gaurav was saying that try to find practical implications of things. So try to do that kind of a work. Definitely, I mean, as a company, we would, I, I'm I I'm very close. I mean, I would want to work with department a lot, and, I mean, and we would want to have students also. So we were also speaking that, if we would want to work with department, if any students are interested in any kinds of internships and all, and, if we can do projects with them, we'll be very happy to do them. So, and at our company also, we have a certain, inclination towards doing and trying to experiment with new things. It's a very small company though. I mean, we have only 20 to 25 people, but we try to ensure that, we keep finding new things, and try to, implement them. So if anyone is interested in working with us, do reach out to me. I mean, I've my details are there with few people. You can ask them.
Ayush, maybe good to spend a few minutes just saying what all you do in your company. I mean, I have an idea, but others may not.
Yeah. So yes, sir. Thanks for pointing out. We see. I mean, the company is called PV Diagnostics, so photovoltaic diagnostics. We are in solar sector. In very simple terms, we started as doctors for solar power plants, and but then we spread out ourselves, and now we are into design engineering, quality control, quality assurance, diagnostics, of course. So our work is completely in solar sector, and we work with various companies to help them with technical side of things, to if their plant performance, plant is not generating up to the desired levels, we work with them to find what can be done to improve the generation of the plant. I mean, we have all kinds of tools that are there, that are required to assess the plants, and in our teams, and we are now also working towards energy storage. So if anyone is interested in working in the energy storage side of things, we'll be very happy to do that. Now a lot of new things are also coming up. uh, Solar storage hybrid, solar wind storage hybrid, so we are also looking to grow into that area. So if anyone is interested, is working around it, we'll be happy to collaborate with them. We have covered about, I mean, we work with all the, to tell you about what is our clientele, we work with all the leading developers that are there in the country, like Renew Power or SoftBank Energy or Tata, Azure Power, sorry, Acme. So all of them that are there, and we we also engage, in fact, in technical due diligence. So helping potential buyers or private equity firms in buying the assets. So from a complete technical perspective. So we have done about 5,000 megawatt of assets across India, covered in different ways. So please do reach out. We'll be very happy to work together. Thank you. Anyone has any questions, we'll be happy to answer.
There seems to be a raised hand, Gautam.
Can I ask a question? Yeah, yeah.
Yeah, hi Gautam.
Ayush, who do you think is your competitor? I know a company who named Smart Helio who is trying to do exactly the same thing as you are.
So we have multiple competitors. I mean, we have so companies like essentially. I mean, right now we are more of a consulting firm, right? And we are developing certain products as well. But from a consulting perspective, we would compete with a DNVGL or a UL or TUV or a Gensol, right? From a product perspective, there are other companies like Smart Helio or multiple other. So I mean, there are good number of companies in India who could be defined as our competitors.
Yeah, got it. Yeah.
Thank you so much, Ayush, for sharing your experience with us and introducing PV diagnostics to us. Moving ahead, we have another alumni, Miss Nilima. Nilima is one of our MTech students. She graduated in 2018 and since then has been working with General Electric. Her work reflects her interests in the field of renewable energy. We would love to hear from her experience as a working professional in the energy sector. Over to you, Nilima.
Thank you, Harshita, for introducing me. Am I audible?
Audible
yes,
but
you
not
are.
visible.
Yeah.
Yeah, that's okay. If your videos, it's okay. Audible is fine.
Okay. So so very good evening to all of you and respected professors and my energy janta. I'm using this word janta after 3 years for my energy people. And it's been 3 years since I left IIT Bombay, but today I'm glad that I got this opportunity to interact with you all. And thank you, Rangan sir, for inviting me. So today I'm going to talk about my personal experience for a couple of minutes. And this is since GE is basically a core company, and usually core company give priorities to core branches only. But if we do research in the areas where core companies are looking for, then it's a big advantage that we can pitch those core sector for us during our placement and all. And during our placement also we took the advantage of the same. And since we had done our electric courses in this core subjects like power electronics, I am from electrical background, so we did courses in power electronics, power system, and our projects were, core oriented. So that was a big advantage that we get it open for us. And since today renewables are holding a good position in the market, not only the solar, wind, hydro, battery, and other hybrid projects are also running across the globe. So it's a plus point for us that we run these courses in our department. We do have solar courses running on, but it's just a small suggestion if we can have a wind courses as well, because in the current renewables market, wind, solar, and hybrids, these are playing the major role. And since I am in GE, so GE, Siemens, Vestas, Suzlon, and there are many other companies who have already stepped into a wind sector. And we are growing very well. And so I'd like to bring the attention towards the wind sector as well. And it will be good if we can explore it. So when I was hired in GE Renewables, I was hired as an EDP. It's a Addition Engineering Development Program. So this is basically a 2 years of program where I have been rotated in 4 different teams, each for 6 months. And I did 4 different projects. First 6 months in electrical team, and then second 6 months in controls team for turbine control software development, running the software in loop, processor in loop, and hardware in the loop for testing and validating the software code. And then I also did my rotation in machine learning. So it was just a 6 months of that I was experiencing the machine learning. It was completely out of the box that I came out, and it was a good experience. But finally, it's just 1 year I boarded in the electrical team, and now I'm working as a grid engineer. And if I talk about the GE renewables, so we do have onshore wind engineering and offshore wind engineering business, and we do have solar projects as well. So And since this is a global organization, so we do have huge competitor in China, Japan, America, and Europe. All those regions we cover 80%. And the smallest, the 20% we cover in like Vietnam, Australia, India, and few of other countries. So basically, I am in onshore wind engineering businesses, and we do have engineering team, projects management team, and execution team. So yeah, in India, in Bangalore, we do have R&D center, and we basically do turbine components designing, its manufacturing, commissioning after site assessment, testing, validation, and certification of the wind turbines. And being a grid engineer, I work for the grid integration to the grid integration and application part. So basically, when you connect the turbine, so before connecting it to the grid, there are certain grid government requirement that you have to meet before connecting it to the grid. These are certain fault right through test or certain kind of frequency response test. So all those testing we perform in the field as well as in the simulations before testing in the field. So we do all this test, and yes, and after passing all those tests, we get it certified from the third party, and then we are allowed to connect to the grid. So this is just a brief intro about my work, and to give you more information about the tools that we are using for these components designing and simulation testing from mechanical perspective. We are using MATLAB, ANSYS, HyperMesh, but in electrical front we are using MATLAB and PSSE, Power Factory, PSCAD. So all these tools we are using here. And yeah, we are also looking for certain research areas since we are dealing with the wind turbines here in GE. So while installation and commissioning, there are certain factors which impacts the turbine, basically the vibration part in the tower and the vibration in the blades while installation, and some of the acoustics, and also like the sensors development and reducing the electrical losses, some 3D printing and blades materials and material strength diagnostic, aerofoils designing. So these are certain research areas that we are developing now. Is there any question?
I guess no question is there. Thank you, Nilima, for giving us some insights into your work. And thank you for your useful suggestions. Now it's a time to reveal winners for the best presentations, followed by the prize distribution. Total 13 prizes will be given, which are sponsored by Forbes Marshall. We are very thankful to Forbes Marshall for this sponsorship. So today we have Dr. Anuradha Ganesh, Director of Research and Innovation, Cummins Technologies Limited, to announce prizes for today's session. I would like to welcome Dr. Anuradha and request her to announce the results.
Okay, so thank you so much for giving me this opportunity. And dear students, I'm really very happy because I'm going to be doing my favorite thing, and that is appreciation. That's really something which I'm very happy about. I know you've all worked very hard and over these months for the project, and last 2 days maybe for the presentation. But I must say you all kept the timelines, and it was excellent presentation. Very well. I attended channel 3 mostly, but I did run through the other channels also, and I noted that the quality of the work as well as the presentation were excellent. I recalled our first energy day many years back, and I must say we have come a long way. Rangan, Shirish, I can congratulate you for that, all of you, the faculty and the students. I was chatting with some of my colleagues. There were many projects which I felt it could be taken to the next level. can be surely transferred for actual application, be it industry or as a tool for decision making for state departments, etc. So a request before I announce the prizes is that to the students, please take that extra mile, travel that extra mile so that your projects are not just stacked on the shelves and actually can be taken forward. With that, I enjoyed my day and I'm very happy to give away the awards. So let me see. Okay. All right. The Channel 1 Awards, which is called as what? Greenhouse was the Channel 1. The first prize goes to Prashant Gupta. So how are we going to do? Are we going to do some prize, or I would love to give some claps for him. Okay. So Prashant Gupta, first prize. Indrajit Mohite, second prize. Indrajit, can we see your face? Where is he? We can't, okay? Right. Yes, and Premanshu Kumar Singh, the third prize. Congratulations to all of you that did a great job. And we move on to Channel 2, Golden Race. Oh, I love the name. Manu Mohan, first prize. Congratulations, Manu. Suren Patwardhan, second prize. Congratulations again, Suren. And Prabhat Ranjan, third prize. Congratulations, Prabhat. Moving on to the third channel, PowerPoint. Lomesh Tikariha, first prize. Congratulations. Manoj Vishwakarma, second prize. Congratulations, Manoj. And I also happened to listen to you. It was very good. And congratulations, Aditi Mahajan, for getting the third prize. Then we have one more channel, and that's Sustainable Solutions. First prize, Amit Upadhyay. Congratulations to you, Amit. Ansari, second prize. Congratulations, Ansari Mohammed. And the third prize goes to Suraj Kanodia. Congratulations, Suraj. And now comes the overall best presenter. Any guesses? Anyone who wants to give me some chat messages on who's the overall best presenter? The overall best presenter for the Energy Day 2021 is Prabhat Sharma. Congratulations, Prabhat. Congratulations to all the winners. Wow, I like that. Let me also do some good bit of clapping. Good. Thank you, and over to you. I really enjoyed these sessions. Thank you so much, students, all of you.
Thank
over
you,
to you.
Yeah, thank you, ma'am, for announcing the results and for being here with us today. Congratulations to all the winners, and we will be distributing prizes in the form of exciting vouchers once the session ends. Now we have a small note of thanks by our overall coordinators of Energy Day 2021. On behalf of the whole organizing committee and chairpersons, I would like to request Mr. Arnav Kamble to please go ahead with it.
Hello, good evening, everyone. Thank you for attending Energy Day 2021. I hope you all had a great time. Firstly, I would like to thank all the presenters who have presented their work, without whom the event would have not been possible. I hope all of you got insights, feedbacks, and suggestions on your work. Then I'd like to thank the organizing team. Just a second. Yeah. So I would like to thank the organizing team. Here are the names of the organizing team: overall coordinators, managers, volunteers. Uh, they have been working for the past 2 months to make Energy Day 2021 a success. I also thank Professor Zakir and Professor Saga Mitra, who have been our mentors and who guided and helped us throughout the course of event and its execution. Lastly, I would like to thank Professor Rangan Banerjee, HOD of the Department of Energy Science and Engineering, for his support to conduct the event. Thank you, everyone. I hope you all had a great time. If Professor Rangan wants to speak.
No, I don't want to say anything unless Zakir or Sagar wants to. Maybe they can say something. Zakir, Sagar, would you like to just say something? If they're there.
No, I think, yeah, Zakir here. So,
Zakir, go ahead.
Yeah, I think everything, I mean, the students have actually said what was required to be said. It was all student-driven event, and the team, particularly which are now highlighted here, have been working tirelessly for the last couple of months. So, a big applause goes to them who have been working very hard. So. Yeah, so we thank everyone, the participants, the students who presented, and others who helped directly or indirectly in this event, which actually helped us to have this event despite the challenges of the time that we have today. Yeah, so thanks to everyone. I think that's what I would say at the end note. With that, I think we can conclude, and unless Sagar has something to add up.
No, it's okay. You can conclude now.
Okay, so thank you all for being with us here today. Now we are closing the session. Thank you again.
Thank you all.
Thank you.
So all the organizers, please stay here. So we want to take on photographs. Switch on everyone's video, all the organizers.
Are we still live on YouTube though?
No, you stop other things. Even department professors also, if you are here, please switch on your video. Rangan was here, I don't know. Zakir?
Yeah, I'm here.
Can you switch on? I think you can ask Rangan and at least chair if they are here. I don't see. Sanjeev?
Yes, sir.
Can you switch on your video? This is the one, only people are there right now?
Yes, sir. Everyone's here.
Sumil? Please switch on your video so you can take a snapshot. Sanjeev, your camera is not on.
One of the devices camera is on, sir. Other one is, I mean, I'm not there.
Okay. So why not you remove that? It looks bad.
Okay, give me a moment. I have to run for that.
Dr. Shaktivel, he wants to be in the frame, he can be. All are here, so you can. All are here, okay. Hey, remove your mask for some minutes. Okay, so all are here. Smile. Smile. That's okay. 1, 2, 3. Done. 1, 2, 3. Done. Thank you. Thank you very much.
Thank you so much, sir.
Thank you.
Thank you, sir. Thank you, sir.
Okay, thank you. Thank you very much.
Thank you, guys. Thanks a lot. Thank you so much.
Thank you, Gautam, for being a part of this event. Your feedbacks have been extremely useful for us throughout the process.
You just contact me anytime on LinkedIn or wherever. Okay. No
Sure.
issues. Yeah.
Definitely.
Yeah. Chalo, bye.
Bye-bye.
Yeah.
Okay, guys. Organizers,
leave it.
you have been it has been primary